Acceleration. Acceleration is more than just a measure of how quickly something speeds up. It's the heartbeat of movement, the invisible force that transforms stillness into action. At its essence, acceleration is the change in velocity over time, a physical whisper that something is shifting, gaining urgency, pushing toward momentum. It is the reason you feel pressed into your seat when a plane takes off, the force that turns a simple stroll into a sprint, the breathless rush in your chest when life suddenly moves faster than you expected. In the physical world, acceleration is governed by Newton's laws, a direct response to the forces around us. Push harder, and the change is greater. Remove resistance, and motion builds with a quiet but unstoppable intensity. This concept isn't just cold math, it's the sensation of a roller coaster's first drop, the pulse of adrenaline as your body braces for the unknown, the thrill of leaning into a curve as gravity and speed wrestle for control. But acceleration is also a metaphor for every turning point in life. It's that electric moment when plans suddenly gain speed, when hesitation evaporates and decisions are made in an instant. It's the force that can lift you toward your goals or hurl you into chaos, depending on how you harness it. You feel it not only in motion, but in the sudden quickening of events, in relationships that evolve overnight, in opportunities that erupt from nowhere. Acceleration reminds us that change rarely happens in silence. It comes with pressure, with force, with a sense of being carried forward whether you're ready or not. It is both exhilarating and terrifying, a constant reminder that the pace of life can shift in a heartbeat, leaving you breathless in its wake. Action. Action is the spark that transforms thought into reality, the moment when an idea steps out of the shadows and demands to be lived. It is movement with intent, a conscious choice to disturb the stillness and bend the flow of events in your favor. At its core, action is the refusal to remain passive, the defiance of letting life simply happen to you. Every great change, every turning point in history began with one decisive action, small or large, that altered the course of everything that followed. In physics, action has its own precise meaning, the integral of energy over time, a quantity that guides the motion of objects and predicts their path through the principle of least action. Nature itself is efficient. It seeks the route of minimal waste, the smoothest journey from one state to another. And yet, in our lives, action often requires confronting resistance, pushing through inertia, and breaking the comfort of routine. There is a certain electricity in action, a pulse that surges through you when you cross the line between planning and doing. It's the feeling of a door swinging open after years of being locked, the rush of stepping onto a stage, the quiet but irrevocable decision to speak when silence feels safer. Action demands courage because it exposes you. It shows the world what you want, what you stand for, and where you intend to go. Without action, dreams decay into distant what-ifs. With it, even the smallest step can trigger a chain reaction, momentum building until the world around you shifts. Action is life-choosing movement over hesitation, and once set in motion, it refuses to be ignored. Adiabatic process. The adiabatic process is the quiet drama of energy transforming in perfect isolation, where heat dares not enter or escape. It is the story of change happening behind closed doors, unseen by the outside world, a transformation driven only by what already exists within. In physics, it describes a system that undergoes a shift, compression or expansion, without any exchange of heat with its surroundings. No warmth flows in, no warmth seeps out, and yet the internal world rearranges itself completely. Imagine air trapped inside a perfectly insulated container. If it is compressed, the molecules are forced closer together, their collisions more violent, and the temperature climbs like a fever born from pressure alone. If the air expands, the opposite occurs. Molecules drift apart, collisions soften, and the temperature falls. a cold born, not from the outside, but from within. There is something hauntingly human in this process, a reflection of how we, too, can change without the world noticing. Sometimes we are compressed by life's pressures, and the heat builds within us, not from outside influence, but from the force of being squeezed into a smaller space than we can comfortably hold. Other times, we expand into new freedom, and a quiet chill settles in, the stillness of a self stretched thin across unfamiliar territory. The adiabatic process is a reminder that transformation does not always require external contact. It is the silent reshaping of the inner world, the way mountains of potential can rise or collapse without a whisper of heat crossing the boundary between you and everything else. It is isolation turned into evolution. Alpha decay. Alpha decay is the slow, inevitable shedding of weight from the heart of an atom, a quiet release of something ancient and powerful. It is the process by which an unstable nucleus lets go of 2 protons and 2 neutrons bound together, the alpha particle, like a sigh that has been held for eons. This release is not a violent explosion, but a patient unraveling, a sign that even the smallest pieces of the universe cannot hold on forever. In the realm of nuclear physics, alpha decay is a mechanism of transformation. A heavy, unstable element, such as uranium or radium, casts off an alpha particle, becoming a different element altogether. This change is irreversible. Once the particle is gone, the atom's very identity shifts. The new element may be more stable, but it is forever altered, carrying the quiet history of what it once was. There is a strange beauty in alpha decay, a sense of dignity in the way matter chooses to lighten itself. It mirrors the human experience of release, the moments when we let go of parts of ourselves, not because we want to, but because carrying them any longer would pull us apart. The energy that escapes in this process is a reminder that even in loss, something powerful is set free. Alpha decay happens slowly, invisibly, over spans of time that make human lives seem like brief flickers, and yet, in its patience, it shapes the world, fuels the Earth's heat, and leaves subtle fingerprints in the form of radiation. It is the universe's quiet confession that even the most solid and enduring things must eventually let go. Ampere. The ampere is the quiet pulse of the invisible river that flows through every wire, every circuit, every machine that hums with life. It is the measure of electric current, the count of how many charged particles rush past a point in a single second. 1 ampere is a steady stream of roughly 6.24 quintillion electrons sliding by, unseen but relentless, like a silent crowd surging toward a destination they will never reach. In the physical world, the ampere is not just a number, it is the lifeblood of technology. It feeds the glow of city lights, powers the engines of trains, and gives breath to the devices we cradle in our hands. Too little, and nothing stirs. Too much, and wires heat, circuits scream, and the air smells faintly of something burning. Between those extremes lies balance, the delicate harmony of control that turns raw energy into something useful. But beyond the physics, there is something poetic about the ampere. It is a reminder that power is not just about potential, it is about movement, about the flow of something that refuses to stay still. Just as a stagnant river is lifeless, so too is an unused charge without the dance of electrons to carry it forward. The ampere hums quietly in the background of our lives, uncelebrated yet essential, a ceaseless march of particles weaving through copper and steel. You cannot see it, you cannot touch it, but you feel its presence in the glow of a screen, the warmth of a bulb, the sudden surge of a motor coming alive. It is the heartbeat of the electric world. Angular momentum. Angular momentum is the stubborn will of motion, the invisible oath an object takes to keep spinning, turning, or orbiting exactly as it is, unless an outside force dares to interfere. It is the swirling persistence that keeps planets, locked in their cosmic dances, figure skaters spinning with breathtaking speed, and galaxies twisting into majestic spirals. In physics, it is the product of an object's rotational inertia and its angular velocity, a measure of how much spin is stored in its very being. What makes angular momentum so captivating is its refusal to fade without reason. Once in motion, it resists change, clinging to its state with a quiet but unshakable loyalty. A spinning top fights to remain upright not because it loves stability, but because the laws of nature bind it to conserve what it already possesses. This is why a collapsing star can spin hundreds of times per second, the same momentum compressed into a tighter, more furious rotation. There is something profoundly human in this principle. We too carry our own angular momentum in the form of habits, emotions, and beliefs, turning endlessly in the orbits we've built for ourselves. When nothing disrupts us, we keep moving as we always have, our paths predictable, our spin unbroken. But when a force enters, a moment of truth, a shift in circumstance, it can redirect our trajectory entirely, sending us into a new arc we never expected. Angular momentum is motion's memory, the echo of a push given long ago, still rippling through the present. It is both a promise and a warning. Once you set something spinning, it will carry that movement farther than you think. Antimatter is the universe's perfect mirror, a reflection so precise it feels almost like a cosmic twin, except that when it meets its counterpart, both vanish in a burst of pure energy. For every particle of matter that builds our bodies, our cities, and our world, there exists an opposite, the same mass, the same magnitude of charge, but reversed in sign. The electron's twin is the positron, the proton's mirror is the antiproton, and together they form the most volatile partnership imaginable. In the realm of physics, antimatter is both elegance and danger. When matter and antimatter collide, their entire mass is converted into energy through annihilation, a release so complete it puts even the most powerful nuclear reactions to shame. This is not destruction in the usual sense, it is perfect transformation, nothing left behind but light. The existence of antimatter raises one of the greatest questions in cosmology. Why does our universe seem to be built almost entirely from matter? In the beginning, the Big Bang should have created equal amounts of both, yet here we stand, surrounded by matter's dominance, with antimatter reduced to fleeting traces in cosmic rays or created momentarily in particle accelerators. There's something haunting about antimatter, like a shadow we can barely touch. It is beauty with a built-in tragedy, a partner to matter destined for mutual erasure, and yet, in its fleeting presence, it offers the purest form of energy release known to science. Antimatter is the promise and the peril of perfect symmetry, the other half of reality, always close, but never able to coexist without burning both halves away in a final blinding embrace. Archimedes' principle. Archimedes' principle is the eternal truth hidden beneath every ripple, the unseen hand that explains why some things float while others sink. It declares that any object immersed in a fluid experiences an upward force equal to the weight of the fluid it displaces. This is not merely a law of physics, it is the poetry of balance, the quiet assurance that the weight you carry will always be met by an equal and opposite lift, if only you are in the right place. Imagine slipping into a still body of water, feeling its cool embrace wrap around you. As your body sinks, the water pushes back, not with anger or resistance, but with an unwavering promise to support you. It is the same principle that keeps massive ships gliding effortlessly across oceans, that lets a child's toy bob on the surface of a pool, that allows submarines to sink with intent and rise again on command. The beauty of Archimedes' principle lies in its subtle justice. The deeper you go, the more water you displace, and the more the water fights to return you to the surface. It mirrors moments in life when the harder you fall, the stronger the forces that rise to meet you. Archimedes is said to have discovered it while bathing, watching the water spill over the edge of the tub as he lowered himself in, suddenly realizing the world had been holding this truth all along. Whether it's a body, a vessel, or a dream, the principle whispers the same promise, that for every weight pressing you down, there exists a force that longs to lift you back up. Atomic number. The atomic number is the identity card of an element, the single defining truth that decides what it is and what it will never be. It is the number of protons in the nucleus, a count so fundamental that changing it rewrites the atom's very name. Hydrogen will always have one. Carbon 6, gold 79. Strip away electrons, cram in more neutrons, and the element still clings to its atomic number as if to say, "This is who I am." In physics and chemistry, the atomic number is more than a label. It is the anchor of the periodic table, the law that arranges the elements in their precise, unshakable order. It dictates the way atoms bond, the colors they burn in a flame, the invisible dances of electrons that determine how matter behaves. It is the root of every chemical reaction, the quiet hand shaping the universe's complexity from a simple integer. Yet there is something deeply human in this principle. The atomic number whispers of identity's permanence, how beneath all change, some truths are unalterable. We can gain or lose, be stripped or remade by life's collisions, but there are core traits that remain untouched, the protons of our being. In the stars, atomic numbers are forged in the heat of nuclear fire, born from chaos and collapse, flung across space as elements waiting to become planets, oceans, and blood. Every atom inside you carries its number proudly, a silent signature written in the core, declaring exactly what it is, unyielding, constant, and eternal. Avogadro's number. Avogadro's number is the universe's quiet, almost mystical head count, the key to linking the invisible world of atoms to the tangible reality we can see and touch. It is the number 602210236.022 times 10^23 hours, an unimaginable quantity representing how many individual particles, atoms, molecules, ions exist in a single mole of substance. It's a bridge between the human scale and the atomic scale, a cosmic translator that whispers, "This is how the microscopic becomes measurable." The enormity of this number is hard to grasp. Imagine counting each grain of sand on every beach on Earth, and you'd still fall incomprehensibly short. Avogadro's number says, in just a drop of water, there are more molecules than there are stars in the known universe. It is a truth that collapses our sense of scale, reminding us that reality is built from an overwhelming abundance of the smallest pieces. This constant is more than a calculation. It is a lens on existence. Chemists use it to weigh the intangible, to predict reactions, to turn the chaos of the unseen into predictable patterns. But on a deeper level, it speaks to the staggering complexity hidden inside the most ordinary things. A breath you take holds billions of molecules once inhaled by ancient forests, by forgotten civilizations, by creatures long extinct. Avogadro's number is humbling. It tells us that even in what feels small, there is an infinity. Every solid, liquid, or gas is an ocean of particles dancing in numbers beyond imagination, all moving to the rhythm of natural law. It is proof that the vastness of the universe exists not only in the stars above, but in the very air between your fingertips. Background radiation. Background radiation is the soft hum of the universe, an invisible echo that never fades. It is the silent reminder that the cosmos has a memory, and it is still whispering its story into the spaces between everything we know. This radiation is everywhere, in the soil beneath your feet, in the air you breathe, even in the food you eat. You cannot hide from it because it is not an intruder. It is a constant, a quiet part of existence. In physics, background radiation comes from two great sources: the natural decay of radioactive materials within the Earth and the faint afterglow of the universe's birth, the cosmic microwave background. The first is the Earth's own breath, the byproduct of uranium, thorium, and potassium slowly breaking apart in the rocks beneath us. The second is something older, almost sacred, the leftover light from the Big Bang itself, stretched and cooled over nearly 14 billion years until it became a faint wash of microwaves surrounding us in every direction. To know about background radiation is to recognize that we are wrapped in history. Every moment of your life is bathed in particles and waves that began their journey long before you existed. It is like standing in a vast cathedral and feeling the lingering vibration of a bell that rang before the walls were even built. It does not harm most of us. It simply exists, a constant presence, unnoticed unless you have the tools to measure it, and yet knowing it's there changes something. It connects you to a story so old and so vast that it humbles every heartbeat, every step, every moment under its eternal, unseen glow. Band gap. The band gap is the silent border between possibility and impossibility, the invisible chasm that determines whether electrons can leap from stillness into motion. In the world of solid-state physics, it is the energy difference between the valence band, where electrons rest, and the conduction band, where they roam free to carry electric current. This tiny space, often measured in mere electron volts, decides the destiny of a material, whether it will be a conductor, an insulator, or something in between. Picture the band gap as a canyon at the heart of every atom structure. In conductors, the canyon barely exists. Electrons flow effortlessly, like water spilling across a flat plain. In insulators, the gap is vast and unbridgeable, trapping electrons in place, locking them in the quiet prison of the valence band. And in semiconductors, the gap is just narrow enough that, with the right push, a photon's kiss, a surge of heat, electrons can break free and dance into the conduction band. This leap is not just a mechanical transition, it is the awakening of potential. It is the moment when stillness bursts into purpose, when something inert becomes alive with energy and movement. The devices that shape our modern world, solar cells, LEDs, microchips, exist because of this delicate balance, this narrow gateway that can be opened or closed at will. The band gap is proof that sometimes the difference between silence and symphony, darkness and light, comes down to a single barrier and the courage or the energy to cross it. It is the space between what is and what could be, waiting for the right spark to make the leap inevitable. Bernoulli's principle. Bernoulli's principle is the quiet truth that speed changes everything, even the weight of the air itself. It tells us that when a fluid moves faster, its pressure drops, a trade-off written into the laws of motion and energy. Air over a wing, water through a narrowing pipe, even the breath that curves the flame of a candle. Each obeys this invisible bargain. It is the reason birds lift into the sky, the secret that keeps a plane aloft, the gentle hand that lets a curved ball dance in midair. In physics, Bernoulli's principle is a direct child of conservation of energy. A fluid has only so much energy to spend. Use more of it for motion, and there's less left for pushing outward. This balance creates pockets of low pressure that pull, lift, and shape the world around them. But beyond its equations, Bernoulli's principle feels like a lesson in the subtle art of influence. It shows how changing speed, not brute force, can reshape outcomes. The faster a river flows, the more it draws in everything along its banks. The quicker a current of air moves, the more it tugs at wings, leaves, and sails, bending their path without a sound. There's beauty in how it works silently, almost invisibly, with no gears or sparks, only the quiet shifting of pressure. It is a reminder that power does not always roar. Sometimes it whispers through movement, altering the course of things simply by flowing differently. In that steady rush, Bernoulli's principle hides the magic of flight, the elegance of motion, and the truth that speed can lift you higher than strength alone ever could. Beta decay. Beta decay is the moment an atom quietly rewrites its own identity, altering the very count of protons in its heart and becoming something entirely new. It is the subatomic drama where a neutron transforms into a proton or a proton into a neutron while flinging away a high-speed electron or positron along with a ghostly neutrino that slips through matter as though it barely exists. This isn't destruction, it's metamorphosis, a delicate but irreversible shift in the nucleus's blueprint. In beta-decay, a neutron feels the pull of instability and fractures into a proton, releasing an electron and an anti-neutrino into the void. In beta-plus decay, a proton surrenders, becoming a neutron as a positron and neutrino are born. Both are whispers of energy and mass transmuting, quiet signatures of the weak nuclear force at work, a force so subtle yet capable of altering the very identity of matter. There is an intimate symbolism here. Beta decay is change from within, driven not by external blows, but by an internal imbalance, too great to ignore. It mirrors the moments in life when something deep inside you decides it can no longer remain the same. The transformation is invisible to the outside world until its effects ripple outward, altering everything. These shifts echo through time. Beta decay fuels the glow of distant stars, shapes the mix of elements in the universe, and leaves traces in ancient rocks that tell the age of the Earth. It is proof that even at the smallest scales, change is inevitable, that identity itself is not fixed, but something the universe rewrites when stability demands it. Binding energy. Binding energy is the invisible glue that holds the universe together, the silent force that decides whether atoms cling tightly or drift apart. It is the measure of how much energy would be required to tear a nucleus into its separate protons and neutrons, the cost of breaking the most intimate bond in the physical world. Without it, there would be no stable matter, no stars, no life, only a chaos of scattered particles, endlessly drifting with nothing to anchor them. In the heart of an atom, protons should repel each other violently, their positive charges screaming to push away, but the strong nuclear force pulls harder, overpowering that resistance. This bond comes at a price. When the nucleus forms, a small portion of its mass is lost, transformed into binding energy according to Einstein's equation EmCO2. That missing mass is not gone. It has become the thread stitching the nucleus together. There is a poetry in binding energy, a truth that extends beyond physics. The tighter the bond, the more it costs to break. The most stable elements, like iron, sit at the peak of the binding energy curve, their nuclei so perfectly balanced that neither fusion nor fission easily releases more energy. Stars live and die by this law, forging lighter elements into heavier ones until they can no longer gain from the trade, collapsing into silence or exploding into brilliance. Binding energy is both strength and vulnerability. It is the hidden price of unity, the reason things endure, and the reason breaking them can unleash forces beyond comprehension. It is proof that even in the smallest corners of the universe, holding on is never without sacrifice. Black hole. A black hole is the universe's most haunting secret, a place where gravity becomes so absolute that nothing, not even light, can escape its grasp. It is the final stage of collapse, the point where matter is crushed into infinite density, and the fabric of space and time bends toward an abyss that has no return. This invisible mouth swallows stars, worlds, and radiation alike, leaving behind only a shadow, a warped imprint on the space around it. At its edge lies the event horizon, the boundary between what can still escape and what is forever lost. Cross it, and every possible path points inward, dragging you deeper, faster, toward the singularity at the heart, a place where the laws of physics themselves dissolve. Here, time stretches into distortion, seconds becoming centuries for the outside observer, while for the one falling, the journey feels inexorable and swift. Black holes are not only destroyers, they are sculptors of galaxies, their gravity pulling stars into hypnotic spirals, their collisions sending ripples through space-time, gravitational waves that echo across the cosmos. They hold mysteries that challenge our understanding, whispering of wormholes, alternate realities, and the possibility that information can never truly die. There is something deeply human in the black hole's pull, a reflection of the moments in life when something grips us so completely that escape feels impossible, like emotions that consume, like obsessions that spiral inward. A black hole draws everything closer, compressing it until all that remains is the essence of what it once was, hidden yet impossibly heavy at the very center of the unknown. Blackbody radiation. Blackbody radiation is the song of heat made visible, the pure and perfect glow of an object that swallows every color yet gives them all back as light. A blackbody is an ideal, something that absorbs all radiation, no matter the wavelength, no matter how faint, holding nothing back. And yet, as it warms, it cannot help but sing its temperature into the universe, releasing a spectrum of light that shifts with its heat. At cooler temperatures, its voice is deep and long, radiating in invisible whispers of infrared. As it grows hotter, the spectrum creeps into the red, the orange, the white-hot blaze, until at unimaginable heat it spills into ultraviolet. This isn't a trick of the surface. It's born from the restless vibration of atoms themselves, from the way energy stirs the very heart of matter until it glows. Blackbody radiation isn't just beauty, it's the key that unlocked the quantum revolution. When scientists tried to predict its spectrum with classical physics, the math broke into infinity, an absurd ultraviolet catastrophe that made no sense. It was Max Planck's daring leap into quantized energy that solved it, a quiet act that changed physics forever. But beyond the equations, blackbody radiation feels almost alive. Stars are black bodies, their light carrying the truth of their temperature across millions of years and miles. Even you, sitting in darkness, are glowing in infrared, your body quietly broadcasting its warmth into the night. It is the universe's confession that heat cannot hide. No matter how perfectly something absorbs, the truth of its energy will always find a way to shine. Bohr Radius. The Bohr Radius is the universe's measure of intimacy, the delicate space between a proton and the electron that orbits it in the simplest atom, hydrogen. It is the quiet balance point where attraction and motion perfectly counter each other. A frozen distance of about 5.29 by 10 to 115.29 times 10 yard 11 meters. In that tiny gap lies the harmony of forces, the pull of the positively charged nucleus trying to draw the electron closer, and the electron's restless motion resisting collapse. It is more than a number. It is the scale on which the architecture of matter begins. Within this minuscule orbit, the laws of quantum mechanics take command, replacing the predictable curves of classical physics with the strange, probabilistic nature of the atomic world. The Bohr radius is the first step into that mystery, a boundary set by nature where stability quietly resides. There's a kind of poetry in its smallness. In this distance, smaller than imagination, entire universes of interaction occur. Energy levels shift, photons are absorbed or released, bonds between atoms are born, and yet it is constant, unwavering, as though the universe carved this rule into the foundation of reality. It's a reminder that stability often comes from an invisible equilibrium, a tension that must be just right for existence to hold together. The Bohr radius is not just the orbit of an electron, it's the quiet promise that even the smallest systems can find balance, that within the vast chaos of the cosmos, there are distances so precise, so perfect, that they allow life and matter to exist at all. Boyle's law. Boyle's law is the intimate dance between pressure and volume, a whispered negotiation where one always yields when the other rises. It tells us that for a fixed amount of gas at a constant temperature, the pressure is inversely proportional to its volume. Compress it, and the pressure swells. Let it expand, and the pressure falls away. It is a law as old as breath itself, as present in your lungs as it is in the depths of the ocean. Imagine holding air in your hands, invisible yet alive. Squeeze it into a smaller space, and the molecules crowd closer, their collisions fierce and relentless, each one adding to the pressure straining against its container. Release it into more room, and the chaos softens. The molecules drift farther apart, striking the walls with less force, their energy still there, but spread thin. This is Boyle's law in its purest form, an unspoken balance that gas must obey. You feel it when you dive underwater and your ears tighten under the weight of the surrounding water, when a sealed bag swells at high altitudes, when your chest expands and contracts with each breath. It is written into the way our world moves and adapts, a constant reminder that space and pressure are bound in an eternal push and pull. There is something profoundly human in Boyle's law, too. Under the weight of life's pressures, we feel compressed, our inner worlds tight and restless. Give ourselves space, and the pressure eases, not gone, but no longer suffocating. Boyle's law is not just a truth about gases, it is a quiet metaphor for the need to breathe, to release, and to make room when the world begins to close in. Buoyancy. Buoyancy is the quiet promise of water and air that no weight is entirely beyond lifting, the invisible upward force that answers every attempt to sink with an equal push toward the surface. It is the reason a ship heavier than a skyscraper can float, why a balloon drifts skyward, why a diver feels lighter the deeper they go. At its heart, buoyancy is the counterbalance between gravity pulling down and a fluid pushing back, a law as old as the oceans themselves. When an object is placed in a fluid, it displaces some of that fluid, and in doing so, it earns the right to be lifted. The displaced water or air pushes upward with a force equal to its own weight, cradling the object in a constant, unseen embrace. This is why steel battleships ride waves effortlessly, and why a feather in the air will slowly find its way down. Different fluids, different balances, but the same unbreakable truth. Buoyancy is not just a law of physics. It is a metaphor for survival. The deeper you sink under the weight of life, the stronger the forces that rise to meet you. It speaks of resilience built into the very nature of existence, a reassurance that there are forces, often invisible, designed to keep you from being pulled under forever. It is a delicate dance. Tip the balance, and you float. Tip it the other way, and you drown. But within that fragile equilibrium lies the beauty of buoyancy, an unyielding reminder that even in the deepest depths, there is always something pushing you back toward the light. Capacitance. Capacitance is the art of holding on to energy without letting it slip away, the quiet patience of a system that stores electrical charge and waits for the right moment to release it. It is measured in farads, but its essence is not in numbers. It is in the tension between what is kept and what is given, in the invisible field stretched between two conductive plates separated by a thin barrier. When a voltage is applied, charges gather on either side like opposing armies staring across a no-man's land, their presence creating an electric field that hums with potential. No current flows across the gap, and yet the energy is there, waiting, compressed, not in space, but in possibility. The greater the capacitance, the more charge can be stored for the same voltage, like a deeper well holding more water under the same surface stillness. In the physical world, capacitors smooth the chaos of electrical signals, hold backup energy for critical moments, and unleash rapid bursts of power when needed. They are the reason your camera's flash can explode in brilliance after a moment's charge, why circuits survive tiny interruptions without going dark, why certain machines breathe in sudden, rhythmic pulses. But capacitance is also a metaphor for restraint and readiness. It is the strength to hold what you've gathered until the moment is right, to contain potential without bleeding it into the void. A capacitor does not squander, it waits, and when the time comes, the release is instant, decisive, and unstoppable, a reminder that stored power, silent though it may seem, is often the most dangerous kind. Carnot Efficiency. Carnot Efficiency is the universe's stern decree on how much perfection you can hope for and how much will always slip away. It is the theoretical ceiling for how efficiently any heat engine can convert thermal energy into useful work, a limit set not by engineering flaws, but by the laws of nature themselves. No matter how perfect your machine, no matter how precise your design, you can never exceed it. It is the quiet reminder that some losses are inevitable. Defined by the temperatures of the hot and cold reservoirs it operates between, Carnot efficiency emerges from the second law of thermodynamics. The greater the temperature difference, the more potential there is for work. But even in the best-case scenario, some energy must be surrendered as waste heat. The Carnot limit isn't a suggestion. It's a boundary etched into reality, one that mocks human ambition with its quiet, immutable certainty. And yet, there's beauty in its inevitability. Carnot efficiency speaks to the deep symmetry of nature, the way energy flows like water down a slope, always toward equilibrium. It tells us that motion, change, and work all come at a price, that perfection is not only unattainable, but unnecessary for progress to unfold. There is a human truth hidden here too. Every effort we make, every transformation we attempt, loses something along the way. Energy leaks into the world in the form of time, mistakes, and sacrifice. But the fact that we cannot reach perfect conversion does not stop us from trying. It drives us to push closer, knowing the limit is there, unmovable, yet still worth chasing. Cathode. The cathode is the giver in the hidden world of electricity, the point from which electrons are born into motion. It is the negative terminal in most electrical devices, the place where energy begins its journey, not with a flash of drama, but with the steady, relentless flow of charge. In a battery, the cathode is where reduction takes place, where electrons are accepted during discharge, pushing life into circuits and bringing machines, lights, and screens to life. In vacuum tubes and old CRT displays, the cathode is heated until it releases electrons in a quiet cascade, a phenomenon called thermionic emission. Those freed electrons surge forward, drawn irresistibly toward the positive anode, carrying with them the potential to create images, sounds, and signals. It is an invisible migration, yet it fuels the glow of history's first televisions, the warmth of early radios, the spark that once connected the world across telegraph wires. There's a quiet poetry in the cathode's role. It is a source, yet it is called negative. It begins the flow not by force, but by offering what it has, letting its electrons go into the unknown. Every current, every hum of a machine, every illuminated screen owes its life to that first release. In chemistry and electrolysis, the cathode becomes the site of transformation, where ions are reduced and new matter takes shape. It is where change is made tangible, metal plated, gases released, elements born anew. The cathode reminds us that beginnings are not always loud or violent. Sometimes they are simply the steady release of what you hold, setting in motion a chain of events that will never return to stillness. Centripetal Force. Centripetal force is the unseen tether that keeps motion from flying apart, the quiet insistence that curves must be held together. It is the inward pull that guides a planet in its orbit, the tension in a spinning rope, the hidden hand steering every turn. Without it, the world would unravel into chaos. Objects in motion would race away in straight lines, abandoning the elegance of circles and spirals for the emptiness of escape. In its essence, centripetal force is not a new force at all, but the direction in which an existing force must act to sustain curved motion. It can be gravity drawing the moon around the earth, friction keeping a car on a bend, or tension pulling a spinning stone toward your hand. Always inward, always toward the center. It is the thread that keeps motion bound to its path. There is something profoundly human in this pull toward the center, a reflection of how in life we too are held by invisible ties. Love, duty, ambition, fear, forces that draw us inward, shaping our trajectories and preventing us from drifting aimlessly into the void. Without these tethers, the arcs we trace would dissolve into unmoored wandering. Centripetal force is both restraint and liberation. Without it, the curve could not exist. With it, the motion becomes endless. It is the reason the stars dance their measured steps, the reason a spinning child can laugh without flying away, the reason a fragile balance between speed and pull can hold a universe together in perfect, breathtaking arcs. Chain reaction. A chain reaction is the unstoppable unfolding of cause into effect, where one small event births another, and then another, until the world is set into motion with a force far greater than the original spark. In physics, it is the essence of compounding events. A neutron striking a nucleus, splitting it into fragments, releasing more neutrons that strike more nuclei, each split multiplying the energy in a surge that grows faster than you can count. It is the beating heart of nuclear power, both the terror and the promise of the atom. In a controlled reactor, a chain reaction hums with precision, releasing heat steadily to light cities and power industries. But remove the brakes and it becomes an inferno, an explosion so swift and vast that matter itself is torn apart in a blinding wave of fire and radiation. Yet chain reactions are not only born in the heart of atoms, they exist in the human world, in rumors that spread like wildfire, in kindness that cascades through strangers, in anger that ricochets until it consumes entire crowds. A single decision, a single word can ripple outward until it no longer resembles its origin, gathering momentum until stopping it is no longer possible. There is something both thrilling and terrifying in this truth. Once a chain reaction begins, it no longer belongs to the one who started it. It becomes its own force, carrying within it the seed of either creation or destruction. One spark, one trigger, and the process accelerates, inevitable, self-sustaining, and utterly beyond recall. Chaos theory. Chaos theory is the unsettling revelation that the universe can be both perfectly ordered and utterly unpredictable at the same time. It is the study of systems so sensitive that the smallest change, a fraction of a fraction, can snowball into consequences vast and unrecognizable. The butterfly effect is its most famous whisper, the idea that a butterfly's wings beating in one corner of the world could set into motion a storm an ocean away. In mathematics and physics, chaos doesn't mean disorder without rules. It means patterns that follow exact laws, yet whose outcomes are impossible to predict beyond a certain point. Weather systems, planetary orbits, population growth, many obey precise equations, but their sensitivity to initial conditions makes them wildly unstable. A tiny difference in the starting point grows until the future is unrecognizable. There's a haunting beauty in this. Chaos theory strips away the illusion of control, reminding us that even in a world of perfect laws, certainty is fragile. We may map the equations, chart the flows, and simulate the patterns, but in the end, life holds too many variables to predict every twist. It is a truth we live every day. A passing conversation changes a life's trajectory. A missed train alters decades of possibility. We are all moving inside chaotic systems where the smallest nudges, often unnoticed, reshape everything. Chaos theory does not tell us to give up on prediction. It tells us to respect the delicate balance of cause and effect, and to never underestimate the quiet, unseen moments that shape the storms ahead. Charge. Charge is the hidden signature every particle carries, an invisible mark that decides how it will interact with the world. It is the reason forces exist between objects that never touch, the unseen hand that pulls some together and drives others apart. In its simplest form, charge comes in two kinds, positive and negative, and the entire architecture of matter rests on the way they attract and repel. Without it, there would be no atoms, no chemistry, no bonds holding the universe in place. At the subatomic level, charge is not just a property, it is a personality. Protons wear their positive charge like a crown, electrons hold their negative charge like a restless fire, and neutrons remain quiet observers with none at all. Yet even in silence, the balance of these charges shapes the structure of everything you see. It is this balance that makes an atom stable, that decides whether elements will unite in harmony or clash in resistance. You can feel charge in the sudden snap of static electricity, in the way your hair rises under a balloon, in the flash of lightning tearing the sky apart. It is a presence you cannot see but can feel in the electric thrill of a storm or the delicate hum of a power device. Charge is more than a scientific term. It is an invisible connection, a constant exchange of invisible threads binding matter together. It reminds us that even when forces are unseen, their influence is undeniable, shaping every interaction in a dance older than the stars, where attraction and repulsion never stop, and nothing is ever truly still. Chemical potential. Chemical potential is the silent currency of matter, the measure of how badly a substance longs to move, to react, to change. It is the energy hidden within particles, not in their speed or position, but in their very willingness to flow from where they are to where they most want to be. Like a restless traveler sensing a better life elsewhere, chemical potential drives atoms and molecules toward balance, pulling them from abundance to scarcity, from pressure to calm. In physics and chemistry, it is the quantity that tells us how a system will evolve, how gases will diffuse, how liquids will mix, how reactions will proceed. When the chemical potential is high in one place and low in another, matter begins its quiet migration, seeking the comfort of equilibrium. This invisible desire fuels everything from the smell of bread drifting through a room to the migration of ions across a living cell's membrane. But chemical potential is more than a mathematical parameter. It's a metaphor for longing. It is the stored possibility inside every system, the tension between what is and what could be. In life, we feel our own version of this pull, the urge to leave comfort for growth, to bridge the gap between current reality and an imagined better state. The beauty of chemical potential lies in its inevitability. Given the right path, movement will happen. It doesn't need a push, it only needs an opening. It is the quiet insistence of nature that imbalance will not last forever, that energy always seeks a way to flow, and that everything eventually finds the place where it belongs. Classical mechanics. Classical mechanics is the grand clockwork of the universe, the set of laws that once promised to predict everything, from the swing of a pendulum to the dance of the planets. It is the physics of motion and force as Isaac Newton saw it, a perfectly ordered system where the past and present determine the future with absolute certainty. In this world, every movement can be traced to a cause, every cause to a law, and every law to a truth written in the fabric of nature. It begins with simple observations. An apple falls, a wheel rolls, a stone skips across water. From these, equations emerge, descriptions of acceleration, momentum, energy, woven into a framework so precise it could guide ships across oceans and predict eclipses centuries in advance. In classical mechanics, the universe feels like a perfectly tuned machine, every gear meshing with another, every motion inevitable. Yet, there is a kind of poetry in its predictability. It reassures us that chaos is an illusion, that beneath the messiness of daily life lies a deep and steady rhythm. To see the world through classical mechanics is to see harmony in motion, the elegance of a planet's orbit, the graceful arc of a thrown ball, the quiet certainty that the same rules binding the stars also govern the fall of a leaf. Even though modern physics has shown its limits at the quantum scale and near the speed of light, classical mechanics still shapes our world. It is the language of engineers, architects, and dreamers who build on Earth's solid laws. It is the promise that motion can be understood, predicted, and, perhaps, mastered. Coefficient of friction. The coefficient of friction is the hidden handshake between two surfaces, the quiet agreement that decides how much they will resist each other's motion. It is a single number, but within it lies the subtle drama of texture, contact, and force, the microscopic hills and valleys that lock together, the invisible bonds that cling and let go, whether it's your shoes gripping the pavement or a glacier dragging across bedrock. The coefficient of friction tells the story of how surfaces interact in the most intimate way. In physics, it is the ratio of the force resisting motion to the force pressing the surfaces together. A high coefficient means stubbornness. Surfaces that cling, dig in, refuse to let go. A low coefficient means slipperiness, ice underfoot, silk sliding against skin, the effortless glide of one thing over another. Yet beneath the simplicity of the number lies a complex interplay of material structure, pressure, and even molecular attraction. On a human level, the coefficient of friction feels like a metaphor for resistance in life. Sometimes we encounter paths that grip us, hold us steady, prevent us from slipping. Other times, we face the treacherous smoothness of situations where control is fleeting and a misstep sends us sliding. The friction we meet shapes how fast we move, how much force we must summon, and whether we stay grounded or lose our footing. It is the reminder that every movement, whether in the mechanical world or the emotional one, meets resistance. And that resistance, though it slows us, also gives us the traction to push forward, to stand firm, and to choose our direction with purpose. Coherence. Coherence is the rare harmony in a world built on chaos, the moment when waves, whether of light, sound, or thought, move together in perfect step. It is not just order, but unity, the kind where every crest and trough align so precisely that the separate parts seem to dissolve into a single powerful whole. In physics, coherence describes the fixed relationship between the phases of waves, a synchrony that allows them to interfere constructively, amplifying their presence instead of canceling each other out. You can see coherence in the sharp, unwavering beam of a laser, where countless photons march in phase, as though bound by a shared purpose. Compare this to the scattered light of a bulb, where every wave moves on its own, unfocused and forgettable. Coherence is why the laser can cut through steel while a lamp can only softly illuminate. It is the difference between scattered noise and united force. But coherence extends beyond light and sound. It lives in the rhythms of nature and the patterns of human connection. It's in the way a flock of birds turns as one in the sky, in the chorus that sings a note so pure it sends shivers through the spine, in moments when two minds align so perfectly that words become unnecessary. Incoherence is easy. It's what happens when signals scatter, when phases drift, when focus slips. Coherence, on the other hand, is fragile and rare, demanding alignment, stability, and purpose. When it happens, it is unforgettable, a force that magnifies everything it touches, turning the ordinary into something piercing, focused, and utterly alive. Compton Effect. The Compton Effect is the moment light reveals it is not untouchable, the proof that even the most ethereal thing in the universe can be struck, deflected, and changed. It is the phenomenon where high-energy photons, tiny packets of light, collide with electrons, losing some of their energy and scattering in a new direction. In that instant, the photon's wavelength stretches, its color shifts, and the electron is jolted into motion, as if light itself had been reminded that it can leave a mark and be marked in return. This discovery shattered the old certainty that light behaved only like a wave, showing instead that it can act like a particle, capable of exchanging energy in sharp, discrete blows. It was a turning point in physics, one of the many cracks in classical theory that let the strange light of quantum mechanics spill through. The Compton effect became undeniable evidence that the universe's rules are written in both rhythm and collision, in both flow and impact. But beyond its equations, there is poetry in the Compton effect. It speaks to the way encounters change us, not just electrons, but people. A single collision, a single moment of contact can alter our trajectory and take something from us, yet also set us in motion towards somewhere new. In the silence of space or the heart of an experiment, the Compton effect whispers a truth. No matter how pure or unshakable something seems, interaction leaves its trace. Light can be struck, paths can be bent, and even the smallest collision can change the story forever. Conservation of energy. The conservation of energy is the universe's unbreakable vow. Nothing is ever truly lost, only transformed. It is the law that declares energy can neither be created nor destroyed, that every burst of light, every rush of motion, every whisper of heat is part of a grand ledger that always balances. Energy changes form. It can become heat, sound, movement, or light, but its total remains constant, as if the universe guards it with an iron will. In the physical world, this law is everywhere. The fall of a hammer turns potential into kinetic, the slam into a spike of sound and warmth. A spark becomes a flame, the flame becomes light and heat, and even when the fire dies, the energy has only scattered into the air and earth. The process is seamless, a constant shape-shifting that never allows something to fade into nothing. But there is something deeply human in this principle. Our own efforts, passions, and choices echo in ways we cannot always see. A kind word becomes confidence. Confidence becomes action. Action becomes change. Nothing we put into the world, good or bad, vanishes. It moves, adapts, and resurfaces in forms we may not recognize. The conservation of energy strips away the illusion of disappearance. It says that endings are never final, that destruction is really transformation, and that what we give, whether heat, light, or love, remains somewhere, always. In a universe that often feels uncertain, this law is a constant heartbeat, reminding us that all things persist, even when they no longer look the same. Conservation of momentum. The conservation of momentum is the universe's promise that nothing moves without leaving its mark, that every push, every collision, every exchange of motion is perfectly balanced in the grand ledger of physics. It is the law that says the total momentum of a closed system remains constant, no matter how violently its parts may crash, scatter, or change direction. Momentum is not destroyed, it is merely transferred, passed like a torch from one body to another. In the physical world, this plays out in every collision, from billiard balls clicking on felt to galaxies merging in a slow, graceful spiral. When two objects interact, the loss of motion in one is the gain of motion in the other, an unbreakable symmetry that binds events together across time. It is nature's refusal to waste movement, its quiet insistence that the sum of motion remains unchanged. There is a deep human echo in this principle. Every action we take imparts momentum. Our choices ripple outward, altering the trajectories of others in ways we may never see. We absorb momentum from the people and events that strike us, redirecting it into new paths, sometimes without realizing the origin of the force that set us in motion. The conservation of momentum reminds us that movement is never isolated. Each push and pull, each exchange of energy links us in an endless chain of cause and effect. The world moves not in fragments, but as an interconnected whole, where nothing we do is ever truly lost. It simply continues transformed in the momentum of everything around us. Convection. Convection is the restless heartbeat of fluids, the endless cycle where heat becomes motion and motion becomes transformation. It is the invisible choreography of rising and falling currents, born from the simple fact that warm matter expands, grows lighter, and rises, while cooler matter contracts, grows heavier, and sinks. In this dance, energy moves not by direct contact or radiant waves, but by the very movement of the medium itself, carrying warmth, carrying change. You can see convection in the rolling boil of water, in the swirling clouds of a thunderstorm, in the slow, grand circulation of molten rock beneath the Earth's crust. It is what stirs the atmosphere into winds, what churns the oceans into powerful currents, what fuels the rising plumes of air that become towering storms. Without it, our world would be still and stratified, with heat locked in place, life and weather frozen into silence. There is an unspoken drama in convection's cycle. The rising is not eternal. Eventually, the heated mass cools and sinks again, making room for something else to rise. The sinking is not permanent. It is only the beginning of another climb. In this, convection becomes a mirror for life itself, where ascent and descent are bound together, each feeding the other in an endless loop. Convection's fingerprints are everywhere. The golden spirals of cream blooming through coffee, the flicker of a candle's flame, the turbulent patterns painted in the sun's surface. It is nature's way of refusing stillness, a reminder that heat longs to move, and that movement, once begun, is a cycle without end. Cosmic microwave background. The cosmic microwave background is the faint afterglow of creation itself, the lingering whisper of the universe's first light. It is the oldest light we can see, born when the cosmos was just 380,000 years old, a newborn compared to its 13.8 billion year lifespan. Before this moment, the universe was a blinding, seething plasma where light could not travel freely, trapped in a dense fog of particles. But as the cosmos expanded and cooled, atoms formed, the fog lifted, and light was finally set free to roam. That light has been traveling ever since, stretched and softened by the expansion of space into faint microwaves, now bathing the entire sky in a delicate, nearly uniform glow, invisible to our eyes but unmistakable to our instruments. The cosmic microwave background is a frozen imprint of the universe's infancy, a snapshot of the moment order began to emerge from chaos. Within its subtle variations, tiny ripples in temperature, lies the blueprint of everything, the seeds of galaxies, stars, and planets, all encoded in a quiet shimmer across the heavens. It is the closest thing we have to a photograph of the beginning, proof that the Big Bang was not just theory, but an event whose echoes still hum all around us. There is something profoundly humbling in knowing that every inch of sky, no matter where you look, carries this faint light. It is a reminder that we live inside the afterglow of our own origin, surrounded by the silent memory of the moment the universe first opened its eyes. Coulomb's law. Coulomb's law is the invisible thread that ties charged particles together or rips them apart. It tells us that electric charges attract or repel each other with a force that grows stronger when they are close and weaker as they drift apart, a dance dictated by both their magnitude and the space between them. Two like charges push each other away. Two opposites pull toward each other. each interaction silent yet relentless, felt across the emptiness between them. In physics, Coulomb's law is as precise as it is poetic. It describes the electric force with a simple truth: double the charge and you double the force. Halve the distance and the force quadruples. It is the law that shapes atoms, binds molecules, and holds matter together on the most fundamental level. Without it, electrons would not cling to nuclei, chemical bonds would crumble, and the structure of the world would dissolve into chaos. But its meaning reaches beyond the realm of particles. Coulomb's law is a reminder that closeness matters, that forces between things grow intense when they are near, whether in attraction or in conflict. Distance softens tensions, while proximity magnifies them, for better or worse. The beauty of Coulomb's law lies in its balance, its symmetry. Every push has its equal pull, every connection its measurable strength, every interaction a precise and predictable weight. And though it is silent, though we cannot see the strings that tie charges together, we live in a world built upon their unseen tension, a constant, delicate pull between separation and union. Critical angle. The critical angle is the exact tipping point where light makes its choice, to break free into the air or to turn inward and never escape. It is the moment in optics when a beam traveling from a denser medium to a less dense one bends so far from the normal that it skims perfectly along the boundary. Beyond this angle, the light does not cross into the other medium at all. It reflects back entirely, trapped in the world it came from. In physics, it is defined by the refractive indices of the two media, a precise threshold calculated by Snell's law. But beyond the math, the critical angle feels like a moment of destiny, the point where the path forward is no longer an option, and retreat becomes the only course. This is the principle that makes fiber optics work. Light guided down thin strands of glass, bouncing endlessly inside, unable to escape. There is a haunting metaphor in this. The critical angle is that instant in life when the conditions change just enough that crossing into the open becomes impossible. Opportunities turn inward, voices that once reached out fall silent, and we find ourselves contained by invisible boundaries we didn't see until we hit them. Sometimes we turn back, not because we want to, but because the laws around us have shifted in ways we cannot defy. It is the fine line between freedom and confinement, escape and reflection, possibility and inevitability. The critical angle is the universe's way of showing that even light, the fastest thing we know, can meet a boundary it cannot pass, and must instead learn to travel within. Critical mass. Critical mass is the tipping point, the exact moment when potential becomes unstoppable reality. In nuclear physics, it is the smallest amount of fissile material needed to sustain a chain reaction. Too little and the reaction fizzles, just enough and it becomes self-sustaining, feeding on itself in an unstoppable surge. It is the threshold where balance shatters, and energy, once contained, begins to cascade beyond control. Imagine a sphere of uranium or plutonium. Each atom sits like a coiled spring, waiting for the right touch, a stray neutron, to split it apart. If the material is below critical mass, most neutrons escape, the reaction dies, and nothing more happens. But reach that precise threshold, and every split releases more neutrons that strike more atoms, creating a runaway sequence that grows exponentially in a matter of microseconds. From that point, there is no turning back. This is the principle that powers nuclear reactors and, in its most destructive form, fuels atomic bombs. The difference lies not in the physics, but in the control, whether the chain reaction is carefully moderated or allowed to roar into violent release. Critical mass is not just a nuclear term, it is a truth that echoes in human life. Movements, revolutions, and ideas often simmer quietly until they hit their own critical mass. Enough people, enough passion, enough momentum, and suddenly they erupt into change. It is the moment when whispers become shouts, when scattered sparks ignite into flame. It is the razor's edge between stillness and detonation, a point where what has been quietly building becomes impossible to contain, and the chain reaction begins. Crystal lattice. A crystal lattice is the frozen music of matter, a repeating pattern so precise it stretches into infinity, binding atoms together in a geometric dance. It is the hidden architecture inside a diamond's brilliance, the reason salt forms perfect cubes, the silent scaffolding that gives metals their strength and minerals their beauty. At the microscopic level, it is nothing but points in space, atoms or ions locked into position, yet together they create a symmetry that can endure for millions of years. In physics, the crystal lattice is more than structure. It is order imposed on chaos. Every point in the lattice holds its neighbor in place, connected by the invisible hands of chemical bonds, repeating the same arrangement over and over like a mantra written in the language of geometry. The distances are exact, the angles deliberate, and the entire arrangement vibrates with the quiet energy of life at the atomic scale. But there is something almost spiritual in a lattice's perfection. It speaks of how stability is born not from isolation, but from connection, how each part exists in its place because of the presence of others. Break the bonds and the pattern shatters, keep them intact, and the structure can survive pressures and temperatures that would destroy lesser forms. The beauty of a crystal lattice lies in its hiddenness. You can hold a gemstone in your hand without ever seeing the infinite repetition inside it, unaware that beneath its surface lies a flawless pattern, patiently repeating itself into the depths, an enduring reminder that some of the most beautiful structures are built quietly, atom by atom. Current. Current is the lifeblood of the electrical world, the steady river of charged particles flowing through metal veins to bring machines, lights, and lives to motion. It is the movement of electrons through a conductor, each one a tiny messenger carrying energy from one point to another. You cannot see it, but you can feel its presence in the hum of a transformer, the flicker of a bulb, the sudden jolt when skin meets an unguarded wire. Measured in amperes, current is the bridge between stored energy and the work it performs. Without it, a battery is just a silent reservoir. With it, the stored charge becomes movement, sound, heat, and light. Direct current flows like a disciplined march, steady, unwavering, while alternating current surges back and forth in a rhythmic pulse that powers cities. Yet current is more than numbers and equations. It is urgency in motion, a restless force that refuses to stand still. Like a river, it finds a path, bending around resistance, surging through narrow channels, always seeking connection. It can be gentle, barely enough to power a whisper of sound, or fierce, enough to tear circuits apart in a crackling blaze. In a way, current mirrors the flow of human connection, ideas, emotions, and influence moving from one person to another. When there is a path, the flow thrives. When there is a break, the movement stops. Current teaches us that energy is only useful when it moves, when it bridges the gap between potential and reality, lighting the dark and setting the silent into motion. Dark energy is the silent breath of the cosmos, an unseen force stretching the very fabric of space itself. It is not matter, not light, not anything we can touch, yet it makes up nearly 70% of the universe. Its presence is known not because we can see it, but because we can see what it does, driving galaxies apart faster and faster, pushing the universe into an ever-accelerating expansion. In physics, dark energy is the name we give to a mystery written into the equations of cosmology. It behaves like a constant pressure, evenly filling space, growing more influential as the universe expands. Where gravity tries to pull matter together, dark energy works in quiet opposition, urging separation, creating more emptiness between the islands of stars. There's something haunting in this idea that the universe's fate is being shaped by something utterly invisible, something that may never be fully understood. Dark energy could be a property of space itself, a hidden field, or a force woven into the geometry of reality. Whatever it is relentless, unstoppable, and everywhere. And like so many things in physics, it mirrors life. Sometimes the greatest changes in our lives are caused by forces we cannot see, only feel in their consequences. Invisible pressures stretch us away from the familiar, expanding the space between what we know and what we have yet to become. Dark energy is the cosmic reminder that the universe is not static, that even in the deepest stillness, there is something pulling us toward a future more vast and distant than we can imagine. Dark matter is the unseen scaffolding of the universe, the invisible weight that shapes galaxies and bends the path of light itself. It neither emits nor absorbs radiation, making it undetectable by any telescope. Yet its gravitational pull is undeniable. Without it, the stars in a galaxy would spin away into the void, unable to cling to one another. Dark matter is the silent architect, holding cosmic structures together in a grip we cannot see, touch, or hear. Its presence is revealed only through its effects, the way galaxies rotate faster than visible matter alone can explain, the way light from distant objects bends and stretches as it passes through unseen masses. Astronomers estimate that dark matter makes up about 85% of all matter in the universe, yet no one knows what it truly is. It could be made of exotic particles that pass through you and me by the trillions every second, leaving no trace except the subtle tug of gravity. There is something haunting in this idea that most of the universe is made of something we have never touched, something we know exists only because of the way it shapes everything else. It is absence with consequence, mystery with undeniable influence. Dark matter is the quiet ruler of the cosmos, hidden in plain sight. It reminds us that reality is never fully contained in what we can see, that sometimes the most powerful forces in our lives are invisible, yet they bind everything together, guiding our paths through a universe we only partly understand. Decibel. The decibel is the measure of sound's power written on a logarithmic scale, a way to capture the vast range between a whisper and a thunderclap without drowning in numbers. It is not sound itself, but the language we use to describe its intensity. The difference between the hush of a library at 30 dB, the chatter of a cafe at 60, and the shattering roar of a jet engine at 120. Each increase of 10 decibels is not a small step, but a doubling of perceived loudness, a reminder that sound grows not gently, but in sudden leaps. Born from the science of telecommunication, the decibel is a tool for measuring ratios of power, giving engineers, musicians, and scientists a common ground to describe the invisible waves that fill our air. But its meaning is felt far beyond formulas. A decibel rating carries the emotional weight of the experience it describes, how a low hum can soothe and how an overwhelming crash can shake you to your bones. In its essence, the decibel is about thresholds. At the quiet end, there is the barely audible, sounds that feel like secrets. At the extreme, there is pain, a reminder that too much energy in the wrong place can damage what we can never replace. Between these lies the entire tapestry of life's noises, laughter, music, storms, applause. The decibel teaches us that perception is nonlinear, that small changes in energy can feel enormous, that intensity is as much about how we experience it as how it is measured. It is the scale on which the soundtrack of existence is written, from the faintest breath to the kind of noise that leaves silence ringing in its wake. Density is the quiet truth of how much matter hides within a given space, the measure of how tightly the fabric of reality has been packed together. It is mass pressed into volume, a number that reveals whether something will sink into darkness or rise to the surface and dance on light. Hold a block of lead in one hand and a block of wood the same size in the other. You will feel density in your bones, the weight that speaks without words. In physics, density is simple. Divide mass by volume, and you uncover its secret. But its implications ripple everywhere. It determines how planets form, how stars collapse, how ships float, and how clouds gather in the sky. It is the reason ice drifts on water while a pebble sinks, the reason air thins as you climb higher until your lungs ache for more. Yet density is more than a physical property. It is a metaphor for substance. Some moments in life feel dense, heavy with meaning, layered with unspoken truths and emotions so tightly packed they bend time itself. Other moments are light, airy, easily brushed aside. The beauty of density lies in its quiet influence. You cannot see it, but you can feel its weight, its resistance, its permanence. It shapes whether something stays or drifts away, whether it settles into the depths or rises toward the open air. In every object, in every moment, density is the unseen hand deciding if it will sink, float, or linger suspended between the two. Diffraction is light's refusal to be confined, its way of bending, spreading, and softening when forced through narrow spaces or around obstacles. It is the quiet rebellion against straight-line travel, a reminder that waves are not rigid arrows. They are fluid, expansive, and capable of painting shadows with unexpected fringes of brightness. When light, sound, or any wave meets an edge, it doesn't simply stop. It curves into the forbidden space, carrying its energy where geometry says it should not go. In physics, diffraction is a direct consequence of the wave nature of reality. A single slit, no wider than a hair, can cause a beam of light to fan out into bands of alternating brightness and darkness, a delicate interference pattern born from the wave's own self-overlap. Oceans curl around jetties, voices seep through doorways, and radio waves bend over hills, all for the same reason. Diffraction is the wave's ability to touch places that seem out of reach. There is a certain poetry here. Diffraction is the soft-spoken truth that boundaries are not absolute. Even when the path is narrow, even when blocked, part of what we are can still slip through, wrapping around obstacles to reach the other side. It is the universe showing us that presence is not always limited by direct access. In the patterns it creates, those delicate ripples of light and dark, diffraction turns barriers into art, edges into opportunities for transformation. It is the bending of paths, the spreading of influence, the proof that movement can continue, not in defiance of obstacles, but because of them. Diffusion. Diffusion is the quiet spreading of possibility, the way order dissolves into balance without force or command. It is the natural process by which particles move from where they are crowded to where they are scarce, driven not by intention, but by the restless randomness of motion. At its heart, diffusion is nature's way of evening the scales, a constant drift toward equilibrium, where concentration no longer has a home to cling to. You see it when the scent of perfume drifts through a room, when a drop of ink slowly blooms through water, when the faint warmth from your skin spreads into the surrounding air. No single particle knows the whole plan, yet together they obey the quiet law, move, collide, wander, until all is even. This is the beauty of diffusion, a transformation born from countless tiny steps, each one insignificant on its own, yet unstoppable in the aggregate. In the human body, diffusion fuels life itself. Oxygen slips from the air in your lungs into your blood, while carbon dioxide drifts out, all without a single conscious effort. Nutrients spread into cells, waste slips away, and the constant exchange keeps you alive without fanfare. There's something profoundly poetic in diffusion's inevitability. It does not rush, it does not force, and yet, given time, it erases all sharp boundaries, turning separation into unity. It reminds us that change often comes not through grand gestures, but through the patient, persistent drift of countless small moments, each moving quietly toward balance until transformation feels like it was always meant to be. Doppler Effect. The Doppler effect is the shifting voice of motion, the way waves change their song depending on where you stand. It is why the siren of an ambulance wails high and urgent as it races toward you, then drops into a lower, fading cry as it speeds away. This isn't a trick of your ears. It's the physics of compression and stretch, of waves bunching together when the source approaches and spreading apart when it retreats. In sound, it is the pitch that shifts. In light, it is the color that drifts. Stars rushing toward us are tinted bluer. Their light waves shorten, while those fleeing into the darkness glow redder. Their waves stretch like cosmic taffy. Astronomers read these subtle shifts as messages from the universe, measuring the speeds of galaxies and the expansion of space itself. The Doppler effect is more than an equation. It's the sensation of change rushing past you, the fleeting moment when something feels intense and close before slipping away into distance. It is a reminder that perception depends on movement, that what we hear or see is shaped not only by the source, but by our own position in the flow. There's a bittersweetness to it too, the way moments in life can feel sharp and vivid as they approach, only to soften as they pass, leaving you listening to the echo. The Doppler effect is proof that motion alters not just the journey, but the way the journey is experienced, changing the song as it moves from now into memory. Drag is the invisible hand that resists motion, the constant reminder that nothing moves through a medium without meeting opposition. It is the force that clings to a swimmer's body, that pushes back against a cyclist's speed, that makes an airplane fight the very air it slices through. In physics, drag is born from interaction, molecules colliding with a moving object, stealing energy from its forward path, turning it into turbulence, heat, and sound. Its nature is complex yet inevitable. The faster you move, the more fiercely drag clutches at you, growing not in gentle proportion, but with a punishing increase that makes high speeds ever harder to maintain. It is the price paid for motion, the tax demanded by air, water, or any fluid that will not simply let you pass unchallenged. But drag is more than a physical force. It's a metaphor for resistance in life. Every pursuit, every ambition meets its own kind of drag, doubt from others, the weight of fear, the friction of obstacles that try to slow your momentum. The harder you push forward, the more those forces seem to grow, testing your will to keep moving. And yet, there is a strange beauty in drag. Pilots and engineers learn not only to fight it, but to work with it, shaping wings, hulls, and surfaces to slip through the resistance with grace. Likewise, in life, drag can shape you, refining your path, teaching you how to move not with brute force alone, but with precision and understanding. It is the unseen adversary that defines the elegance and cost of speed. Drift velocity. Drift velocity is the slow, deliberate march of electrons through a conductor, the hidden current beneath the illusion of instantaneous power. When you flip a switch and a light floods the room, it feels as though electricity moves at the speed of thought, but in truth, each individual electron creeps forward at a pace almost lazy, their progress measured in millimeters per second. The brilliance of the bulb is not the speed of the particles themselves, but the chain reaction of their movement, like a line of dominoes falling nearly at once. In physics, drift velocity is the average velocity that a charged particle, such as an electron, attains due to an electric field. It is governed by the current, the number of charge carriers, and the cross-sectional area of the conductor. The electrons may drift slowly, but their collective push sends energy racing at a fraction of the speed of light, carrying power through homes, cities, and worlds. There's something deeply human in this quiet slowness. We live in a culture obsessed with speed, yet drift velocity reminds us that even a slow, steady movement can power something far greater than itself. The current doesn't require each electron to rush. It only needs them to move together, aligned by the same force. It is the physics of patience. The small steps, repeated endlessly, become unstoppable motion. Drift velocity is the invisible reminder that progress is not always about racing forward. It can be the steady advance of countless tiny parts, moving together until the light turns on and the world changes in an instant. Elasticity. Elasticity is the quiet promise of return, the ability of something to bend, stretch, or compress, and then find its way back to where it began. In physics, it is the property of a material that allows it to store energy when deformed and release it when the force is gone, as though it remembers its original shape and refuses to forget. It is the snap of a rubber band, the rebound of a trampoline, the way a bowstring hums back to rest after sending an arrow into flight. On a molecular level, elasticity is a dance of bonds. Stretch a material, and its particles shift apart, tension building like a held breath. Release it, and the bonds pull tight again, reclaiming their place. This recovery is not always perfect. Stretch too far, and the bonds break, leaving only the ghost of the original form. But within its limits, elasticity is a graceful resilience, a willingness to endure disturbance without permanent change. In the world around us, elasticity shapes more than toys and sports gear. It governs the recoil of metals, the flex of bridges in the wind, the gentle give of your skin. It's there every time you walk, as tendons and muscles stretch and contract in effortless rhythm. Elasticity carries a quiet metaphor. Strength is not only in resisting change, but in yielding to it and then recovering. It is the reminder that sometimes survival means absorbing the strain, bending when you must, and knowing deep in your structure that you can find your way back, whole again, when the pressure fades. Electric field. An electric field is the invisible reach of a charge, the unseen influence that stretches out into space, tugging on anything with an opposite or like charge. It is the quiet pressure you cannot touch, yet always feel in its effects, the force that makes a strand of hair rise toward a comb, that drives lightning to leap from cloud to ground, that guides electrons through the veins of a circuit. Like a ghostly wind, it pushes and pulls without ever making contact, shaping the motion of charged particles in its grasp. In physics, the electric field is defined as the force per unit charge, a map of how a lone positive test charge would be pushed or pulled in every point of space. Around a single charge, its lines radiate outward or inward like the rays of an unseen sun. Between opposites, they bridge the gap in smooth arcs, binding the two in constant tension. But beyond diagrams and formulas, the electric field is a metaphor for unseen influence. It's the way one presence can alter the behavior of everything around it without ever touching it directly. The unspoken pull of a leader in a room, the magnetic draw of someone's gaze, the tension in the air before a storm. The beauty of the electric field lies in its permanence and reach. A charge cannot help but create it. It extends outward endlessly, fading but never truly vanishing. It is the silent reminder that even the smallest presence can shape the space around it, leaving an imprint on everything that dares to come close. Electromagnetic induction. Electromagnetic induction is the magic trick of motion turned into electricity, the quiet alchemy that lets movement create power without a single spark of fuel. It is the phenomenon discovered by Michael Faraday in 1831 when he found that moving a magnet through a coil of wire stirs electrons into motion, birthing an electric current from nothing more than the shifting embrace of a magnetic field. In physics, it is simple yet profound. Change the magnetic field around a conductor, and charges will stir as if awakened from sleep, flowing in response to the invisible hand of magnetism. This is how generators breathe life into cities, how wind turbines transform air into light, how hydroelectric dams turn the pull of water into the hum of electrical grids. But electromagnetic induction is more than a technical marvel. It is a reminder that change itself is power. A static field does nothing. Only motion, only variation creates the spark. It tells us that potential is meaningless until it is disturbed, that energy comes alive when the environment shifts, when something moves through what once seemed still. Every time a train roars past and lights flicker from the nearby rails, every time your phone charges wirelessly through the subtle interplay of coils and fields, you are witnessing this quiet miracle. It is the heartbeat of modern civilization, humming unseen in transformers, motors, and countless devices. Electromagnetic induction is proof that in the right conditions, motion and magnetism can weave together, conjuring energy from the very act of change itself. Electromotive force, or EMF, is the invisible push that drives electric charge into motion, the spark that turns potential into flow. Despite its name, it is not truly a force, but a kind of pressure, an energy per unit charge that urges electrons to move through a circuit. It is the heartbeat of batteries, generators, and the countless devices we depend on, a hidden source that whispers to every electron, "Go." In physics, EMF is measured in volts, the work done to move a unit of charge from one point to another. In a battery, it comes from chemical reactions that separate charges, building an electric tension that aches to be released. In a generator, it's born from the dance of magnetic fields and moving conductors, Faraday's law made tangible. No matter the source, EMF is the origin point, the quiet cause behind every flicker of light, hum of machinery, or surge of data. There's a profound metaphor in it. EMF is potential energy waiting for connection, like ambition before opportunity or emotion before expression. It is the stored power within us, invisible until the circuit of our lives closes and we find the path for it to flow. Without EMF, a circuit is just a hollow loop, complete in shape but lifeless in function. It reminds us that motion always begins with a push, a cause, an imbalance aching to be resolved. Whether in the currents of physics or the currents of our own lives, electromotive force is the unseen will that transforms stillness into motion and potential into reality. The electron is the restless wanderer of the atom, a tiny particle carrying a negative charge, forever in motion yet bound to its nucleus by invisible forces. It is almost weightless compared to protons and neutrons, yet it shapes nearly everything we see, touch, and feel. Electrons define the chemistry of matter, the colors of the world, the very way atoms bind together into the structures of life. In physics, the electron is fundamental. It cannot be broken into smaller parts, a true building block of nature. It moves in regions we call orbitals, not fixed paths, existing as both particle and wave. It can leap between energy levels in an instant, releasing light as it falls, absorbing energy as it climbs. This flicker between states powers everything from the glow of neon lights to the photosynthesis that fuels the living world. Electrons carry the flow of electricity, drifting through wires to light our homes, power our machines, and connect us across continents. They are the lifeblood of technology, yet they also shape the simplest moments: the static spark on your skin, the shimmer of a soap bubble, the shine in a loved one's eyes under warm light. There is something mysterious in their dual nature, tangible enough to measure, yet so small they defy our everyday sense of reality. They are both everywhere and nowhere, slipping through the spaces of the universe in silent obedience to quantum laws. The electron is proof that the smallest things can hold the greatest influence, that even the tiniest wanderer can shape the fate of stars, worlds, and the lives unfolding beneath them. Electron affinity. Electron affinity is the quiet hunger of an atom, the subtle longing it feels when offered an extra electron. It is the energy released when that stray negative charge finds a home, settling into the outer shell like a long-lost piece clicking into place. Some atoms welcome the newcomer eagerly, releasing energy in a warm rush. Others resist, their structures too crowded or unstable to let it in without cost. In physics and chemistry, electron affinity is measured in energy per mole, a numerical reflection of how much an atom wants to grow its family of electrons. Elements like chlorine, with their nearly complete outer shells, embrace the extra electron with open arms, releasing energy as if in gratitude. Metals, in contrast, often have little desire for more. They would rather give electrons away than take them in, like travelers shedding weight for the road ahead. But beyond the data, electron affinity speaks of compatibility and desire. It is the story of attraction at the smallest scale, where stability is the ultimate goal. A high electron affinity is a sign of an atom that knows exactly what it wants and will transform itself to get it. It mirrors the human tendency to seek what completes us, to welcome what fills the empty spaces in our lives, and to release energy, joy, or relief when we finally find it. Electron affinity is proof that even in the cold logic of atomic structure, there exists a kind of yearning, a pull toward balance and wholeness that nothing in the universe is too small to feel. Electron volt. The electron volt is the smallest whisper of energy with the power to shape the universe, a unit born from the intimate relationship between electricity and motion. It is defined as the energy gained or lost by a single electron when it moves through an electric potential difference of 1 volt. In human terms, it is unimaginably tiny, just 1.6 by 10 191.6 times 10 919 joules. Yet, in the quantum world, it is vast enough to measure the steps of particles, the glow of stars, and the secrets of atoms. In physics, the electron volt is not about brute force. It is about precision. It measures the delicate nudges that shift electrons into higher orbits, the exact energy needed to free them from atoms, the subtle thresholds at which particles collide and create something entirely new. High-energy physics speaks in millions or billions of electron volts, measuring the violence inside particle accelerators and the birth of particles unseen in nature. But there is something poetic about the scale of the electron volt. It reminds us that the universe's most profound changes often come from the smallest pushes, just enough energy to tip the balance, to break a bond, to create light where there was darkness. Every photon of light your eyes see carries its energy in electron volts, its color determined by that value. From the warmth of a candle flame to the lethal brilliance of gamma rays, all are simply variations of this same quiet unit. The electron volt is the currency of the subatomic world, the measure by which the tiniest events echo into cosmic consequences. Entropy. Entropy is the quiet drift of the universe toward disorder, the measure of how energy, once pure and focused, inevitably spreads out, losing its ability to do useful work. It is the slow unspooling of structure into chaos, the reason a hot drink cools, a wound-up spring unwinds, and stars burn through their fuel until they fade. In thermodynamics, entropy quantifies this tendency, a natural law that says time moves in one direction, from order to disorder, from possibility to inevitability. At the microscopic level, entropy is the count of all possible ways a system can arrange itself, with higher entropy meaning more randomness, more ways to be without being organized. Left alone, systems wander toward this state, not because order is forbidden, but because disorder is vastly more probable. A sandcastle will not build itself. A shattered glass will not leap back together. The past is forever locked because entropy grows with every passing moment. And yet, entropy is not merely decay. It is the story of change. It drives the mixing of air you breathe, the spread of light across the sky, the transformation of energy from one form to another. Life itself exists in defiance of entropy locally, building intricate structures by consuming energy and increasing disorder elsewhere. There's an ache in knowing that, in the long run, entropy wins, that every star will dim, every structure crumble, every flame go out. But there is also beauty in the fleeting order we create along the way, the delicate patterns we carve into the current before it carries us into the great, inevitable stillness. Equilibrium. Equilibrium is the moment when opposing forces find perfect balance, when motion and change slow into stillness, not because nothing is happening, but because everything is happening in equal measure. In physics, it is the state where all influences cancel each other out, where a system settles into harmony with itself. It can be static, like a rock resting motionless on the ground, or dynamic, like a planet endlessly circling its star, always moving, yet never drifting away. On the molecular level, equilibrium is a constant negotiation. In a chemical reaction, it's the point where reactants turn into products at the same rate that products return to reactants. Nothing looks different, yet every moment is alive with exchange. Push matched by pull, gain matched by loss. It is the hidden hum of balance that keeps the system unchanged to the naked eye. Equilibrium is not only a physical truth, but a deeply human one. We feel it in moments when life stops swinging wildly between extremes, when chaos and control strike a fragile peace. It is the calm after storms, the steady breath after a long run, the weightless instant when a scale hangs perfectly level. But equilibrium can be fleeting. A small disturbance, a gust of wind, a sudden thought, a single unexpected force can tip it toward motion again. It reminds us that balance is not absence of activity, but a living tension that must be maintained. In this delicate state, equilibrium becomes both a comfort and a warning. Harmony is possible, but it is never immune to change. Escape velocity. Escape velocity is the ultimate threshold of freedom, the exact speed an object must reach to break free from a planet's gravitational embrace forever. It is not simply about going fast. It is about outrunning the pull of an invisible tether, crossing the point where no force will drag you back. For Earth, this speed is about 11.2 kilometers per second, an instant of unimaginable acceleration that severs the bond between you and home. In physics, it is born from a perfect balance between kinetic energy and gravitational potential. If your motion carries just enough energy to match the pull of gravity, you will climb endlessly, slowing but never stopping until the planet shrinks into a distant memory, fall short, and you will arc back, pulled into the familiar embrace you tried to leave. Escape velocity is more than a calculation. It is a metaphor for the moments when we break free from the forces that have shaped and confined us. It is the courage to gather enough momentum, emotional, mental, or physical, to push beyond fear, doubt, or expectation. And just like in physics, the heavier the tether, the greater the effort required to break it. There is beauty in its precision. No extra speed is needed, no waste of energy, just the exact amount to carry you into the infinite. Escape velocity is a reminder that freedom, whether from a planet or a past, is not about running endlessly, but about finding the perfect moment, the perfect push to cross the boundary into the vastness beyond. Faraday's Law. Faraday's Law is the elegant promise that changing magnetism will always give birth to electricity, a truth that binds motion, magnetism, and current into one unbreakable relationship. It declares that when the magnetic flux through a loop of wire changes, whether by moving the magnet, reshaping the loop, or altering the field, an electric current is induced, as if the wire itself feels the change and responds with life. Discovered by Michael Faraday in 1831, this law became the heartbeat of modern technology. It is why generators spin in power plants, why transformers hum quietly on poles, why your phone can charge without a wire. A moving magnet and a coil need no fuel, no flame, only the invisible dance of fields, trading motion for electricity in a seamless exchange. The mathematics are precise, relating the induced voltage to the rate of change of magnetic flux. But the essence of Faraday's law is more than numbers. It is about transformation, how the unseen can be turned into the tangible, how motion can be captured and stored as energy. The faster or more dramatically the magnetic environment changes, the stronger the electrical response, as if nature rewards change with power. There is something deeply symbolic in this. Faraday's law tells us that it is not the static that generates energy. It is change, disruption, movement. Without a shift, there is silence. With it, there is current, light, and motion. Every flicker of electricity in your life, from the streetlight's glow to the hum of a computer, carries within it the quiet truth Faraday uncovered, that in change there is power. Fermion. A fermion is nature's building block with a stubborn sense of individuality, a particle that refuses to share its exact quantum state with another. Governed by the Pauli exclusion principle, fermions are the reason matter has structure, the reason you can't fall through the floor, why atoms have layered shells, and why the world is not a ghostly blur of overlapping particles. Electrons, protons, neutrons, these are all fermions, each carrying mass, spin, and an unwavering insistence on being distinct. In physics, fermions are defined by their half-integer spin, values like 12 frac or 32 frac 3t, and this property shapes their behavior. Unlike bosons, which can pile into the same quantum state without protest, fermions draw invisible boundaries, creating the very framework of matter. This exclusion forces electrons into different orbits, stacking like rungs on a ladder, giving chemistry its complexity and the universe its variety. There is a deeply human poetry in the nature of fermions. They remind us that individuality creates structure, that the refusal to occupy the same place as another can give rise to stability, form, and balance. Without this principle, there would be no solid matter, no planets, no bodies to hold our consciousness, only a formless sea of sameness. Fermions are the quiet architects of reality. They move unseen, obeying rules written deep into the language of quantum mechanics, yet their collective behavior builds the tangible world. Every object you've touched, every breath you've taken, every heartbeat you've felt exists because fermions stand their ground, holding their place in the grand arrangement of existence. Fission is the splitting of the indivisible, the moment when the heart of an atom tears itself apart and releases energy on a scale that defies the imagination. It begins deep within the nucleus of a heavy atom like uranium-235 or plutonium-239, where the delicate balance between the strong nuclear force and the electric repulsion of protons is already strained. A single neutron can tip that balance, striking the nucleus and shattering it into smaller fragments, freeing more neutrons and unleashing an immense burst of energy. This chain reaction can be a controlled hum, as in a nuclear reactor where the release is carefully moderated to produce steady power for cities and industries, or it can be an unrestrained roar, the force behind the devastating brilliance of an atomic bomb, where the reaction races beyond control in millionths of a second. The energy of fission is born from the binding energy that once held the nucleus together, energy that lay dormant for billions of years until the moment of release. Along with the fragments, radiation pours out, invisible but potent, leaving both promise and danger in its wake. There is a haunting duality to fission. It can illuminate homes or destroy them, extend the reach of human civilization or end it. It is proof that the smallest things in the universe can hold unimaginable power, and that our understanding of nature's secrets is both a gift and a responsibility. Fission is the crack in the armor of the atom, the opening of a door that can never truly be closed once we've stepped through. Force is the silent command that changes motion, the invisible hand that pushes, pulls, and shapes the path of everything in the universe. It is what turns stillness into movement, redirects the flight of a comet, or holds a bridge steady against the wind. Defined in physics as mass times acceleration, force is the bridge between matter and change. The reason objects do not simply drift untouched through existence, but interact, collide, and transform. It can be a gentle nudge or an unstoppable surge. The same principle governs the light touch that sends a pendulum swaying and the crushing pressure inside a star's core. Gravity, friction, tension, magnetism. These are all forces, each with its own personality, its own way of influencing the world. Without them, there would be no structure, no order, only endless, aimless drift. But force is more than a mechanical quantity. It is the essence of influence. In life, we feel invisible forces just as real as those in physics. Love that pulls us closer, fear that pushes us away, ambition that drives us forward. These forces, too, change our direction, shape our momentum, and alter our destinies. The beauty of force lies in its inevitability. Apply it, and something must respond. No object, no matter how still, is immune. It is the language of interaction, the truth that nothing exists in isolation. Whether in the fall of an apple or the birth of a star, force is the unseen link between cause and effect, the constant reminder that motion is never born without a reason. Fourier Transform. The Fourier Transform is the key that unlocks the hidden languages within signals, the lens that lets us see not just what something is, but what it's made of. At its core, it is a mathematical spell that takes a complex, tangled waveform, whether it's sound, light, or any fluctuating signal, and reveals the individual pure tones or frequencies woven into it. It is like hearing every instrument in an orchestra separately while still understanding the full symphony. In physics, engineering, and beyond, the Fourier Transform is everywhere. It takes vibrations from a guitar string and shows the precise frequencies that give it its unique timbre. It analyzes light to reveal the chemical makeup of distant stars. It deciphers seismic tremors to understand the Earth's restless movements. It can even compress images and audio, distilling them into their essential patterns for storage and transmission. What makes it extraordinary is its ability to translate between time and frequency, the when and the what of a signal. In the time domain, a heartbeat looks like a series of pulses. In the frequency domain, those same pulses become a spectrum, revealing rhythms hidden to the naked eye. But beyond the math, the Fourier Transform carries a truth about perception itself. Complexity is just simplicity in disguise. Beneath every chaos of sound or light, there is order, clear tones, repeating waves, patterns that, once seen, change how you understand the whole. It is a reminder that the world is built from layers, and sometimes the only way to see its beauty is to take it apart and listen to each note separately. Frequency. Frequency is the pulse of repetition, the steady heartbeat of a wave as it cycles again and again through time. It is the number of times a pattern completes itself in a single second, measured in hertz, a count of rhythm written into the language of physics. Whether it is the flicker of light, the vibration of a guitar string, or the rise and fall of your own breath, frequency tells us how often something repeats, how fast the invisible pattern is dancing. In physics, frequency defines the character of a wave. A low frequency means slow, rolling cycles, deep ocean swells, the rumble of distant thunder, the slow swing of a pendulum. A high frequency is rapid and sharp, blinding blue light, piercing notes, the shiver of atoms in intense heat. It is the difference between a whisper and a scream, between a gentle ripple and a violent vibration. But frequency is more than a number. It is rhythm itself, the tempo of the universe. From the spinning of electrons to the orbits of planets, from the ticking of a clock to the beating of a heart, frequency connects events across scales so vast they seem unrelated. There's something almost intimate about it. Frequency is how the world keeps time, how waves of sound carry meaning, how light encodes color, how signals bridge the gap between machines and minds. It is a reminder that existence itself is not static, but a constant repetition, a ceaseless oscillation, life unfolding in patterns, always moving to the quiet, unseen beat beneath it all. Friction. Friction is the quiet resistance that meets every step, every turn, every attempt to move. It is the invisible hand that grips two surfaces together, opposing their motion and turning raw movement into heat. Without it, our world would be unrecognizable. Feet could not grip the ground, cars could not steer, tools could not hold. Yet with it, energy is always lost, motion always slowed, as if the universe taxes every act of movement. At the microscopic level, friction is the meeting of jagged landscapes. Even the smoothest surfaces are rough under a microscope, their peaks and valleys catching against one another. Push one object over another, and those microscopic edges collide, bend, and break, releasing tiny bursts of heat in the process. Sometimes molecular attraction adds its own hold, making the resistance stronger, as if the surfaces were reluctant to part. You can feel friction in the warmth of your palms after rubbing them together, in the squeal of brakes, in the slow wearing away of stone under a river's flow. It is both a safeguard and an obstacle, the reason you can climb without slipping, yet also the force that grinds away at moving parts until they fail. There's a human truth in friction as well. Every interaction, every movement through life meets resistance. Some of it steadies us, keeps us grounded. Some of it wears us down. Friction reminds us that progress is never without costs, that even in the smallest motions, there is always something to overcome, and in that overcoming, heat and change are born. Fundamental force. A fundamental force is one of nature's unshakable pillars, the deep, invisible currents that hold the universe together and make every interaction possible. These are not forces we build or invent. They are woven into reality itself, irreducible and absolute. There are four we know: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each is distinct, yet all are threads in the same cosmic tapestry, governing how matter moves, binds, and transforms. Gravity is the gentle but relentless pull that shapes the paths of planets and cradles galaxies in its grasp. Electromagnetism is the force of attraction and repulsion between charges, responsible for light, magnetism, and the chemistry of life itself. The strong nuclear force is the most intense of all, binding protons and neutrons in atomic nuclei with unyielding strength. The weak nuclear force is subtle but transformative, enabling radioactive decay and fueling the reactions that power the sun. These forces act across scales so vast and so small that we rarely think about them, yet they dictate everything from the birth of stars to the flicker of a neuron in your brain. Without them, matter could not form, light could not travel, and time itself might unravel. There is a kind of reverence in knowing that all complexity, every breath, every ocean, every thought, depends on these few, simple rules. Fundamental forces are the quiet monarchs of the cosmos, their reign absolute, their presence constant, and their influence stretching from the heart of the atom to the edge of the universe. Gravitational field. A gravitational field is the invisible fabric stretched around every mass, the quiet influence that bends the path of anything that dares to enter its domain. It is not a force in itself, but the stage on which gravity performs, a map of how any object would be pulled if it wandered into range. Every star, planet, and speck of dust drapes space in its own field, a constant whisper calling other masses closer. In physics, the gravitational field is described as the force per unit mass at any given point, but this sterile definition hides its elegance. Imagine the sun's field, a vast, unseen net holding Earth in its orbit, curving the trajectory of comets and guiding the dance of planets as if they were beads sliding along taut, invisible threads. Even black holes possess fields so steep and unforgiving that not even light can climb out once it crosses their horizon. The beauty of the gravitational field is that it needs no contact to reach you. It acts from a distance, its influence woven into the very geometry of space-time. Step closer, and the pull grows stronger. Drift away, and it weakens, but it never fully disappears. It is a constant reminder that presence alone can shape the world. Just as mass shapes its field, people too carry invisible influences, gravity of character, of thought, of emotion, that draw others near or hold them in orbit. The gravitational field is the universe's way of saying that nothing, no matter how small, exists without leaving its mark on the space around it. Gamma rays are the universe's most intense whispers of energy, invisible beams that carry the raw, unfiltered violence of cosmic events. They are photons, just like the light that warms your skin, but with energy so high they can pierce steel, pass through flesh, and alter the very structure of matter. Born in the heart of radioactive decay, in the collision of subatomic particles, and in the explosions of dying stars, gamma rays are the purest expression of energy unleashed. In physics, they sit at the extreme end of the electromagnetic spectrum, beyond X-rays, beyond ultraviolet, each gamma photon packing millions of electron volts. Their wavelengths are unimaginably small, their frequency so high that they vibrate with a power capable of reshaping atoms themselves. Nuclear reactors produce them, so do black holes, neutron stars, and supernovas, where gravity and energy push matter to its absolute limits. Yet there is a duality in gamma rays. They are destroyers, capable of tearing through DNA, igniting chemical chaos in living cells, but also healers, used in targeted cancer treatments to burn away what nothing else can touch. They are a paradox of creation and destruction, as beautiful as they are dangerous. Gamma rays remind us that the universe does not deal in gentleness alone. Its brightest lights are often born in violence, its most potent tools capable of both salvation and ruin. They are proof that energy, in its most concentrated form, carries no morality. It simply is, waiting for someone or something to decide how it will be used. Gauss's law. Gauss's law is the elegant truth that electric fields are not chaotic wanderers, but follow a precise balance, flowing outward from electric charges like ripples from a stone dropped into still water. It states that the total electric flux through any closed surface is directly proportional to the net charge enclosed within it. In simpler terms, the amount of field escaping a surface depends only on what's inside, not on the shape or complexity of the surface itself. In physics, it is one of Maxwell's 4 equations, the pillars of electromagnetism, distilling the complexity of electric forces into a single, unshakable principle. Picture an invisible bubble around a cluster of charges. Gauss's law tells you that every electric field line crossing that bubble begins or ends on a charge within and nowhere else. The outside world's twists and distractions cannot alter that sum. There's a quiet, almost spiritual symmetry here. Gauss's law is a reminder that influence comes from within, that the true source of what radiates outward is found in the heart of the system, not in its external decoration. The surface may warp and change, but the field it carries is born from what lies inside. In the realm of nature, this law keeps order in the invisible architecture of forces. In the realm of metaphor, it is the truth that what we project, our energy, our influence, our presence, is determined by the charge we hold at our core. The shape of the container may change, but the essence of what escapes into the world is always the sum of what we carry within. General relativity. General relativity is Einstein's grand rewriting of gravity, not as a force pulling objects together, but as the bending of space and time themselves. In this vision, the universe is a vast fabric, and every object with mass presses into it, curving it like a heavy ball on a trampoline. Other objects move along these curves, not because they are pulled, but because the very shape of the space they travel through has been altered. It explains why planets orbit stars, why light bends around massive galaxies, why time itself runs differently depending on where you stand. Near something massive, space is warped more sharply, and time slows, a subtle stretching of reality that has been measured with atomic clocks and seen in the bending of starlight during eclipses. General relativity is not just an abstract theory. It has reshaped how we understand the cosmos. It predicted black holes, regions where space and time curve so steeply that nothing, not even light, can escape. It revealed that the universe is not static, but expanding, its very fabric stretching over billions of years. Even your phone's GPS relies on corrections from general relativity, because satellites orbit in a slightly different flow of time than you do on Earth's surface. There is something deeply humbling in general relativity. It tells us that space is not an empty stage and time is not a steady beat. They are intertwined, flexible, and alive, changing with the presence of matter and energy. Gravity, in this light, is no longer a mysterious pull. It is the shape of the world itself, guiding everything along its unseen curves. Gravitational potential. Gravitational potential is the quiet tension between an object and the pull of a massive body, the stored promise of motion that exists simply because of position. It is the energy you hold by being somewhere in a gravitational field, the invisible pressure of the Earth's pull on a stone resting at the edge of a cliff, or the silent binding between a planet and its star. In physics, gravitational potential is measured as energy per unit mass. How much work could be done if that mass were allowed to move freely? Lift an object higher, and its potential grows. Bring it closer to the center of gravity, and it falls, trading potential for kinetic energy in a smooth, inevitable exchange. This trade is the choreography of orbits. The reason moons circle planets, planets circle stars, and comets dive in brilliant arcs before returning to the dark. There is something haunting in the concept, an acknowledgement that stillness is never truly still. Even when motion pauses, the possibility of movement remains, waiting for a moment of release. A stone at the top of a hill is just as bound to the Earth's will as one falling toward it. The difference lies only in whether that potential has been spent. Gravitational potential reminds us that position is power. Where you are shapes what you can become, just as an object's place in a field shapes the energy it holds. It is a silent, constant force, always present, always pulling, waiting for the moment when restraint turns into motion and the stored promise is finally set free. Gravity. Gravity is the silent tether binding everything in the universe, the invisible hand that pulls matter toward matter, shaping the paths of planets, the arcs of falling apples, and the swirl of galaxies across cosmic time. It is the weakest of the fundamental forces, yet its reach is infinite, guiding the dance of stars and holding you steadfast to the earth. Without it, there would be no orbits, no tides, no structure, only a drifting chaos where nothing stays close for long. In physics, gravity is described by Einstein's general relativity not as a pull, but as the bending of space-time itself. Massive objects warp the fabric of reality, and smaller ones follow the curves they create. The Earth orbits the Sun, not because it's being pulled in the traditional sense, but because space is shaped like a vast, invisible funnel, and Earth's motion is forever guided along its contours. Even light, the fastest thing we know, cannot resist bending to this shape. Gravity is more than mechanics, it is connection. It is the reason the moon tugs at the oceans, the reason stars are born in collapsing clouds of gas, the reason galaxies remain bound in elegant spirals instead of dissolving into the void. There's a quiet poetry in its persistence. Gravity never sleeps, never fades with distance enough to disappear completely. It is the universe's way of keeping its pieces close, of ensuring that no matter how vast the separation, there is always a pull, a reminder that everything is linked and nothing truly drifts alone. Half-life. Half-life is the clockwork heartbeat of decay, the measure of how long it takes for half of something unstable to disappear. In physics, it is the time required for half of the atoms in a radioactive substance to transform into something else, shedding particles, releasing energy, and quietly changing their identity. It is not a countdown to sudden extinction, but a slow, relentless fading, a rhythm that can stretch from fractions of a second to billions of years. Imagine a pile of uranium atoms, each one like a ticking clock with no sound, no visible motion, yet all bound to the same law. After one half-life, half of them will remain. After another, only a quarter. The decay never stops, but it never finishes completely either. Each step leaves something behind, the ghost of what once was. Half-life is written into the deep history of the Earth, powering the heat in its core, marking the ages of rocks and fossils through radiometric dating. It is the reason nuclear waste remains dangerous for millennia, and why certain isotopes linger in the body long after exposure. It is time measured not by the rising and setting of the sun, but by the transformation of matter itself. There is something both haunting and comforting about the half-life. It is predictable, unwavering, immune to haste or delay. It speaks to the inevitability of change, not in sudden bursts, but in the steady erosion of what exists, until one day, without realizing it, you are looking at something entirely new. It is the quiet mathematics of impermanence, written into the very atoms of the universe. Heat capacity. Heat capacity is the measure of how much warmth a substance can hold before it begins to change, the quiet resilience of matter against the touch of heat. It is the amount of energy needed to raise its temperature by a single degree, a reflection of how stubbornly it clings to its current state. Some materials, like water, have an immense heat capacity, soaking up energy like an ocean absorbing sunlight without quickly growing hotter. Others yield easily, their temperature climbing with the smallest whisper of heat. In physics, heat capacity reveals the hidden personality of matter, how its atoms and molecules respond when energy tries to stir them into faster motion. In a solid, tightly bound particles may resist change, passing energy along their rigid lattice. In gases, freer particles leap to higher speeds with less persuasion, shifting the temperature more rapidly. Yet beyond the formulas, heat capacity carries a deeper metaphor. It speaks to endurance, the ability to absorb change without immediately showing it, to take in life's surges and hold them quietly until the moment they finally transform you. A person with a high emotional heat capacity can face waves of chaos without burning up. One with less may flare with each small spark. The beauty of heat capacity is in its quiet patience. It does not rush to change. It takes the time to gather energy, to hold it, to let it seep inward before revealing its effect. It is a reminder that some transformations are slow and deep, and that what seems unmoved on the surface may be quietly storing the power to shift entirely. Heisenberg Uncertainty Principle. The Heisenberg Uncertainty Principle is the unsettling truth that, at the most fundamental level of reality, precision has limits. It tells us that you cannot know both the exact position and exact momentum of a particle at the same time. The more sharply you pin down where it is, the more its motion blurs. The more clearly you define how fast and in what direction it moves, the more its location dissolves into uncertainty. This is not a flaw of our tools, it is the way the universe is built. In quantum mechanics, particles are not solid marbles rolling through space, but waves of probability, their existence spread out until an observation forces them into a single outcome. This principle means there is no perfect map of the microscopic world, no hidden variables to reveal a complete picture. Reality itself is smeared in possibility until the moment of measurement, and even then, certainty exists only for one aspect at a time. There is something profoundly human in this law. It reflects the limits of our understanding, the way life itself resists total prediction. We may know someone's path, but not their exact place upon it, their position in a moment, but not where they are headed. The closer we focus on one detail, the more the others slip away. The Heisenberg uncertainty principle is both humbling and liberating. It shatters the dream of perfect control and replaces it with a world of probabilities, where mystery is not just a gap in knowledge, but a built-in feature of existence, a reminder that the deeper we look, the more reality flickers between knowing and not knowing. Hooke's law. Hooke's law is the promise that within certain limits, the more you stretch or compress something, the harder it will pull back, an unspoken pact between force and displacement. It states that the force exerted by a spring is directly proportional to how far it is stretched or compressed, expressed in the simple equation F psi kxf e psion kx. The minus sign is the spring's quiet rebellion, a reminder that its force always acts to restore balance, pulling toward equilibrium no matter which way you disturb it. In the physical world, this law governs more than springs. It shapes the behavior of elastic materials, determines the oscillation of pendulums, and defines the vibrations of musical strings. Stretch a bow, compress a shock absorber, bend a diving board. Hooke's law is there, translating every distortion into a measured, restoring force. There's a human reflection in this principle. We too have our limits of resilience. Push someone gently, and they may yield, but the further you pull them from their center, the stronger the resistance to return. Hooke's law captures that hidden yearning for equilibrium, the pull to return to a state of rest after tension or strain. Yet it also warns that beyond a certain point, the elastic limit, the pact breaks. The spring won't return, the material won't heal, the balance won't be restored. Hooke's law is the physics of stability, but also the truth of fragility, that all systems, no matter how resilient, have a threshold beyond which they are changed forever. Hubble's law. Hubble's law is the revelation that the universe is not standing still, it is stretching, and everything is moving away from everything else. At its heart, it says that the farther a galaxy is from us, the faster it is receding, its light stretched into longer, redder wavelengths by the expansion of space itself. It is not motion through space in the usual sense, but the space between galaxies, growing like the surface of an inflating balloon, carrying them apart. This discovery shattered the idea of a static cosmos. When Edwin Hubble measured the faint smears of light from distant galaxies in the 1920s, he saw a pattern. Their light was redshifted in direct proportion to their distance. It was as if the universe itself were breathing outward, a steady expansion that had been happening since the moment of its birth. Hubble's law is not just an observation, it is a key to the past. If the universe is expanding now, then long ago it must have been smaller, denser, and unimaginably hotter. Follow this thought backward far enough, and you arrive at the Big Bang, the singular event that began time and space as we know them. There is something awe-inspiring and a little lonely in Hubble's law. Every galaxy outside our local group is slowly vanishing from our reach, its light stretched and dimmed by the very fabric of reality. In the far future, the night sky will grow emptier, not because the stars are dying, but because the universe is carrying them beyond the horizon of sight. It is the law that reminds us everything we know is part of an endless, silent drift into the unknown. Impulse is the sudden transfer of force over time, the quick, decisive push that can change an object's motion in an instant. It is the punch of a bat meeting a ball, the jolt of brakes stopping a speeding car, the sharp shove that sends a still object into motion. In physics, impulse is the product of force and the time it's applied, a bridge between raw force and the momentum it leaves behind. What makes impulse unique is its brevity. It doesn't linger. It strikes and is gone, yet its effects can be lasting. A short, powerful burst of force can create the same change in momentum as a gentle push stretched over a long period. It's why a hammer's swing is effective, not because it's constant, but because it delivers energy in a focused, concentrated moment. Impulse is more than a mechanical event. It's the embodiment of turning points in life. Sometimes change doesn't arrive slowly. It comes all at once, in a single moment that alters your path forever. It's the unexpected phone call, the decision made in seconds, the chance encounter that sends your life in a new direction. These moments are short in duration, but heavy in consequence, just like the collisions and bursts of force that shape the motion of physical objects. There is beauty in impulse's swiftness. It reminds us that not all transformation requires time. Some only need the right strike at the right moment with the right intensity. And once that moment arrives, it leaves a momentum you carry long after the contact has passed. Inductance. Inductance is the quiet resistance to change, the stubborn memory of an electrical circuit that refuses to let current shift without consequence. It is the property of a conductor, often a coil, that stores energy in a magnetic field whenever current flows through it. And when that current tries to change, inductance pushes back, releasing its stored energy in a surge, as if to say, "I will not let you move on so quickly." In physics, inductance is measured in henries, and its strength depends on the coil's turns, its core, and its geometry. The more inductance a circuit has, the more it resists rapid changes in current. This is not resistance in the form of heat, but resistance in time, a delay, a smoothing, a memory. Motors, transformers, and countless electronic systems depend on inductance to manage energy flow, to store it in fields and return it when needed. But there is something almost poetic in its behavior. Inductance teaches that movement carries inertia, even in the invisible world of electrons. Once a flow begins, it wants to keep going. Once it stops, it does not vanish instantly, but leaves a trace, a parting gift of energy that lingers in the air. We see this principle reflected in life: habits that resist sudden change, momentum that refuses to halt the instant we decide, emotions that echo long after the moment has passed. Inductance is proof that even in the silence of circuits, there is memory, there is resistance, and there is the undeniable truth that change, no matter how small, always comes with a push and a pull. Inertia is the quiet stubbornness of matter, the deep-seated reluctance to change whatever state it's in. If something is at rest, it wants to remain still. If it's moving, it wants to keep moving, gliding forward along the same path unless something forces it to stop or turn. It's not resistance born from malice or fatigue. It's simply the nature of mass to preserve its motion, a silent loyalty to the state it already knows. In physics, inertia is embodied in Newton's first law of motion, the principle that an object's velocity will not change unless acted upon by an external force. The greater the mass, the greater the inertia, and the harder it is to push, stop, or redirect. It's why a heavy boulder resists your shove, and why a speeding train can't halt instantly. It carries with it the momentum of everything it has been doing up to this moment. But inertia is more than a physical property. It's a mirror to human life. We all carry our own kind of motion, habits, routines, ways of thinking that can be just as hard to alter as the path of a planet. Sometimes this stability protects us, keeping us steady against passing disruptions. Other times, it traps us, making change feel impossible even when we need it most. Inertia reminds us that change requires a push, sometimes from the outside, sometimes from deep within. Without that nudge, we will keep moving as we are, for better or worse, drifting on the same course until something finally compels us to turn. Interference. Interference is the meeting of waves in a shared space, the moment when they overlap and decide, for an instant, whether to build each other higher or tear each other down. It is a law of patterns, where the rise and fall of one wave aligns or misaligns with another, creating shapes of startling beauty or silence. In physics, interference can be constructive, where crests meet crests and amplify into brilliance, or destructive, where crest meets trough and they cancel into nothing. You can see it in the ripples of water when two stones are thrown into a pond, the circles colliding to form a shifting lace of peaks and valleys. You can hear it in the trembling beat of two musical notes just out of tune, their sound waves weaving in and out of phase. Light, too, reveals its wave nature through interference, producing shimmering rainbows on soap bubbles or the delicate colors of an oil slick, where thin layers bend and blend light into patterns too intricate for the eye to fully follow. Interference is more than a physical effect. It's a reminder that encounters can magnify or diminish what exists. When two forces meet in harmony, the result is something greater than either could achieve alone. When they meet in opposition, they can cancel each other entirely, leaving only stillness in their place. It is the poetry of alignment and misalignment, the unseen negotiation between rhythms, energies, and paths. Interference shows us that the way things meet matters as much as their individual strength, and that even the smallest meeting of waves can change the pattern of the whole. Ionization energy. Ionization energy is the measure of how fiercely an atom holds onto its electrons, the cost of prying one away from its orbit. It is the minimum energy needed to remove an electron from a neutral atom in its ground state, a precise figure that reveals the atom's stubbornness or willingness to let go. High ionization energy means the atom guards its electrons like treasure. Low ionization energy means it parts with them almost casually. In physics and chemistry, this value is shaped by the pull of the nucleus and the distance between that core of protons and the electrons it claims. In small atoms with strong nuclear charge, electrons are drawn in tightly, clinging as though their very existence depends on it. Larger atoms, with electrons farther from the nucleus and shielded by inner shells, release them more easily, their grasp looser and more forgiving. Yet ionization energy carries a metaphor that extends beyond the atom. It is about attachment and the effort it takes to break it. Some bonds, whether atomic, emotional, or personal, require immense energy to sever, as if every force in the universe conspires to keep them intact. Others can be broken with the lightest touch, as though the connection was never meant to last. There is something revealing in knowing an atom's ionization energy. It is the story of what it values, what it will fight to protect, and what it will relinquish under the right pressure. It is a reminder that letting go in nature and in life always comes at a cost, and that the price says everything about the bond. Isotope. An isotope is the same element wearing a different weight, a subtle variation in the core of an atom that changes its mass, but not its identity. Every atom of an element shares the same number of protons, its atomic number, the unshakable fingerprint of what it is. But isotopes differ in the number of neutrons tucked beside those protons in the nucleus. Some are light, some are heavy, yet all share the same chemical soul. In physics and chemistry, isotopes are both ordinary and extraordinary. Stable isotopes endure for billions of years, quietly existing in the air we breathe, the water we drink, and the bones in our bodies. Radioactive isotopes, however, live on borrowed time, shedding particles and energy in their march towards stability. This decay can be gentle, measured in half-lives longer than human history, or violent, releasing bursts of radiation in moments. Their uses are as varied as their forms: tracers mapping blood flow through the human body, tools for dating ancient fossils and rocks, fuels for nuclear reactors, and even weapons of unimaginable power. Each isotope carries a unique balance of stability and energy, a combination that can heal or harm, illuminate or destroy. But isotopes also speak to the quiet truth that identity can hold steady while the inside shifts. Two atoms of carbon, one light and eternal, the other heavy and unstable, will both bond, burn, and behave the same chemically, yet inside, their hearts tell different stories. An isotope is proof that change does not always alter who you are. Sometimes it simply changes how long you will last. Joule. A joule is the quiet currency of energy, the single precise measure of how much work has been done or heat has been transferred. It is defined simply: 1 joule is the work required to apply a force of 1 Newton over a distance of 1 meter. But in that simplicity lies the scale of all motion, all heat, all transformation in the physical world. Every flicker of a light bulb, every gust of wind, every heartbeat can be traced back to exchanges measured in joules. In physics, the joule unites force, distance, and time into one universal language of energy. Whether it's the kinetic energy of a thrown ball, the potential energy of water held behind a dam, or the heat radiating from a sunlit wall, all can be quantified in this same unit. It's the bridge between motion and warmth, between mechanical work and the quiet vibration of atoms. There's an elegance in its universality. A joule is as real in the microcosm as it is in the cosmos. It tells us that the spark inside a tiny LED and the surge that launches a rocket share the same fundamental currency, only the amounts differ. And like the passing of coins through countless hands, joules are never truly lost. They shift form, kinetic to thermal, potential to light, moving invisibly from one place to another. The joule is a reminder that energy is constant, always in circulation, weaving every action, every warmth, every movement into the same vast and unending economy of the universe. Kelvin is the language of temperature stripped bare of human reference, the pure scale that begins at the coldest point the universe will ever allow. Unlike Celsius or Fahrenheit, Kelvin does not measure heat against the shifting benchmarks of water's freezing or boiling. It begins at absolute zero, the place where all motion in atoms ceases, where energy sinks into stillness so deep that nothing can be colder. From there, it rises without degrees of warm or cold, only a measure of how much energy vibrates in matter. At 0 K, molecules are locked in place, stripped of all thermal motion, a silence so complete it exists only in theory. Nature can approach it, but never quite touch it. From that base, every increase in Kelvin is a step upward in the ceaseless motion of particles. The hum of atoms at room temperature, around 293 K, the violent collisions inside stars, soaring into the millions. Kelvin is the scale of scientists and the cosmos, the standard for measuring the heat of distant suns, the chill of interstellar space, the energy in fusion reactors. It removes the comfort of human context, giving numbers that feel alien, until you remember they are reality's true measure. There is something haunting about Kelvin. It reveals that our warmest days, our coldest nights, are tiny fluctuations on a vast ladder of energy that stretches from near nothingness to the raging heart of stars. It is a reminder that temperature is not just sensation, but the pulse of the universe itself, measured from the silence at its floor to the roaring heat at its peak. Kinetic energy. Kinetic energy is the pure expression of motion, the living proof that movement itself carries power. It is the energy an object possesses simply because it is in motion, a store of possibility that grows with both mass and speed, a rolling boulder, a falling raindrop, a planet hurtling through its orbit. All are vessels of kinetic energy, their movement holding the potential to shape, strike, or transform whatever lies in their path. In physics, kinetic energy is measured by the equation 12 mV basasam frac combo 1 2 mvvl2, a deceptively simple formula that hides a truth both elegant and dangerous. Speed is not just linear, it is squared. Double the speed and the energy quadruples. This is why a soft toss feels harmless, but the same object thrown faster can shatter glass, break bones, or carve valleys into planets. Yet kinetic energy is more than numbers. It is the heartbeat of every chase, the rush of wind in your hair, the feeling of being propelled forward by something larger than yourself. It is the proof that motion is never idle, that every step, every leap, every orbit is storing a kind of power that can be released in an instant. There is a certain poetry in knowing that even the smallest particle racing through space carries with it the ability to alter the world on impact. Kinetic energy is the universe's way of saying that movement is never meaningless, that every motion, no matter how small, holds within it the potential to change everything it touches. Kirchhoff's laws. Kirchhoff's laws are the quiet rules that keep the chaos of electricity in order, the twin principles that ensure every circuit, no matter how tangled, obeys the logic of balance. They state first that in any closed loop, the total voltage gained and lost must sum to zero. Energy is conserved, always returned to the ledger. Second, that at any junction, the total current flowing in must equal the total current flowing out. Charges do not vanish, they only pass through. In physics, these laws are deceptively simple, but endlessly powerful. With them, you can untangle the snarl of a complex circuit, predict how current will split among countless branches, and trace the exact path energy takes from source to load. They are the quiet accountants of electricity, tallying every drop of charge, every push of voltage, ensuring nothing escapes unnoticed. But Kirchhoff's laws are more than math. They are a reflection of balance in all systems. They remind us that what flows into a place must, in some form, flow out, that gains must be paid for, that nothing moves without leaving a trace elsewhere. Whether in the hum of a city's power grid or the delicate heart of a microchip, these laws whisper the same truth. The universe keeps its accounts perfect. There are no loopholes, no debts that vanish into nothing. Everything is carried, measured, and returned, just as every force and choice in life ripples onward, finding its way back into the endless loop. Lagrangian. The Lagrangian is the poet's version of physics, a single mathematical expression that distills the motion of a system into the difference between its kinetic and potential energy. It is the heartbeat of the principle of least action, the idea that nature, in all its complexity, chooses the path that minimizes effort, the route of deepest elegance. Within its form lies the power to describe everything, from a falling apple to the orbits of planets, from vibrating strings to the ripples of space-time itself. In mechanics, the Lagrangian is written as Litvleost vi, where TT is kinetic energy and VV is potential energy. It is deceptively simple, yet through the Lagrange equations, it generates the laws of motion without directly invoking forces. Instead of asking, what is pushing or pulling, it asks, what path honors the balance of energy most perfectly? The answers it yields are the trajectories we see written across the universe. There is a quiet beauty in its philosophy. The Lagrangian does not obsess over every push and pull. It steps back, looking at the whole journey, then whispers the simplest, most harmonious way forward. It is nature's preference for grace over waste, for paths that seem inevitable once taken. And in this, it mirrors life. Often we seek the shortest or easiest path, but the Lagrangian reminds us that the truest path is the one that balances all energies at play, momentum and potential, speed and position, into a single, fluid story. It is motion told as poetry, written in the language of balance. Laser. A laser is light made perfect, pure, focused, and relentless. Its name, born from light amplification by stimulated emission of radiation, hides the quiet poetry of what it truly is. Countless photons, identical in color, phase, and direction, marching in absolute unison. Unlike ordinary light, which scatters in every direction, a laser is coherence given form, a beam so disciplined it can cross vast distances without losing its edge. The heart of a laser is a medium, gas, crystal, or semiconductor, whose atoms are excited into a restless energy. Then comes the trigger. One photon nudges an excited atom, prompting it to release another photon exactly like itself. This twin triggers more and more still until the beam is a cascade of perfect copies, each reinforcing the others. Contained between mirrors, the light bounces back and forth, growing in intensity until a narrow doorway lets it escape, not as a flood, but as a single, unwavering blade of light. Lasers are both delicate and formidable. They scan barcodes in grocery stores, perform surgeries with hair-thin precision, carry information through fiber optic cables at the speed of light, and cut through steel with a heat so concentrated it seems to defy nature. There's a certain awe in knowing that this power comes from order, not chaos. A laser's strength lies in unity, every photon aligned, every wave and phase, every direction the same. It is the embodiment of focus, proof that when countless small energies move together with perfect discipline, they can carve through distance, darkness, and matter itself without ever wavering. Lepton. A lepton is one of nature's most elusive citizens, a fundamental particle so small it cannot be split into anything simpler. It is part of the bedrock of the universe, existing in 6 known varieties: the electron, muon, tau, and their ghostly counterparts, the neutrinos. Unlike quarks, leptons do not feel the strong nuclear force that binds protons and neutrons. They live on the fringes of that power, interacting instead through electromagnetism, the weak nuclear force, and gravity. The electron is the most familiar lepton, weaving through atoms to form the chemistry of life. But the neutrino is the most mysterious, born in nuclear reactions in stars, supernovae, and even the Big Bang itself. It passes through planets, people, and entire galaxies almost without notice. Billions of neutrinos stream through your body every second, silent and unseen, as if the universe were breathing through you. Leptons are the quiet architects of matter's behavior. Without them, atoms could not exist, electricity could not flow, and the radiant light of the sun could never reach us. They are both ordinary and extraordinary, so woven into our daily lives that we forget their presence, yet so untouchable that we may never hold one in our hands. There's something humbling in the lepton's nature. It reminds us that the most essential parts of existence are often invisible, that reality is built not only by the forces we can see, but by the faint, persistent work of particles that slip through the world without leaving a trace, except for the fact that without them, nothing would be here at all. Light year. A light year is not time at all. It is distance, vast beyond ordinary comprehension. It is the measure of how far light, moving at 299,792 kilometers per second, will travel in the vacuum of space over the course of 1 Earth year. In that span, a single beam crosses nearly 9.46 trillion kilometers, stitching together a thread of pure speed across the dark. In astronomy, the light year is a ruler for the infinite. It measures the yawning gap between stars, the aching stretch between galaxies, the space where human journeys become dreams. When we say a star is 10 light years away, we are really saying we see it as it was 10 years ago. Its light has traveled that entire time to reach our eyes. In every distant glow is a time capsule, an echo of the past moving toward us without pause. The light year humbles us. It reveals that the night sky is not a picture of now, but a layered history written in photons. Some of the stars we admire may already be gone, their final light still on its way, traveling faithfully across the cold, yet the light year also inspires. It is the bridge that allows us to see across the universe, to witness galaxies millions or even billions of years old. It turns distance into story, into proof that light itself is a messenger carrying the memory of places we may never touch. To measure in light years is to admit that space is not empty. It is filled with journeys still unfolding, each beam of light a traveler older than our civilizations. Lorentz transformation. The Lorentz transformation is the universe's way of bending reality to keep the speed of light untouchable, no matter how fast you move. It is the set of equations that reshape space and time themselves when objects approach relativistic speeds, ensuring that the laws of physics remain the same for all observers. Distances contract, clocks slow, and simultaneity, the idea that two events can happen at the same time, dissolves into a matter of perspective. In physics, the Lorentz transformation bridges two frames of reference moving relative to one another, adjusting their measurements of space and time so that light speed stays constant. If you travel close to light speed, your seconds stretch longer, your lengths shrink, and events that seem ordered to you might appear reversed to someone else. This isn't an illusion. It's reality as dictated by special relativity, a truth woven into the fabric of the cosmos. There's something dizzying, almost disorienting about it. The Lorentz transformation doesn't just change numbers, it alters what is real for each observer. Two people can witness the same universe and yet measure its moments and distances differently, both entirely correct in their own frame. It carries a quiet human echo as well, the reminder that perspective shapes reality. The same events can look different depending on where you stand and how fast you're moving through life. The Lorentz transformation is the cosmic proof that truth can be relative, not because reality bends for convenience, but because space and time themselves are not the fixed absolutes we once believed, but a fluid stage shaped by motion. Magnetic field. A magnetic field is the unseen architecture of force surrounding magnets, electric currents, and even planets, shaping the space around them in ways both gentle and immense. It is not a physical object you can touch, yet it exerts a pull and push that guides charged particles, bends their paths, and organizes chaos into invisible patterns. Its presence is traced in the arcs of iron filings around a bar magnet, the shimmering auroras at Earth's poles, and the steady hum of compasses pointing north. At its heart, a magnetic field is born from motion, specifically the movement of electric charges. An electron spinning in its tiny orbit creates a whisper of magnetism. A river of electrons flowing through a wire builds a stronger field that can loop, twist, or stretch far into space. The field's lines form closed loops, circling endlessly from one pole to the other, as if magnetism itself refuses to have loose ends. Earth's magnetic field is a planetary shield, born from molten iron churning deep within its core. It deflects solar wind, protecting our atmosphere from being stripped away, and in doing so, protects life itself. Without it, the surface would be bathed in lethal radiation, the sky stripped bare of its protective blue. There is a quiet mystery in magnetic fields. They are invisible, yet they shape the world with certainty. They remind us that not all forces announce themselves loudly. Some simply exist, guiding, guarding, and influencing everything within their reach, whether we notice their presence or not. Mass is the measure of how much matter an object holds, the quiet weight of existence itself. It is not just heaviness, it is substance, the amount of stuff that makes something what it is. Mass gives objects their inertia, their resistance to changes in motion, and it anchors them within the pull of gravity. It is why a boulder resists being pushed while a feather yields with ease, why planets hold moons in orbit, and why stars gather their light into blazing spheres. In physics, mass comes in two intertwined forms: inertial mass, which measures how strongly an object resists acceleration, and gravitational mass, which measures how strongly it interacts with the gravity of other bodies. The beauty is that these two are not separate, they are the same, a truth woven into the very structure of the universe and proven with every falling apple and orbiting planet. Mass is also a kind of stored energy, as Einstein revealed with EmC2e equals mCO2, a reminder that what we call matter can, under the right circumstances, become pure energy of unimaginable magnitude. The sun shines because mass is transformed in its core, piece by piece, into the light and heat that bathe our world. But beyond equations, mass feels like permanence. It is the tangible proof that something is here, that it occupies space and exerts influence simply by existing. In a universe where so much is fleeting, light racing past, particles winking in and out, mass is a declaration of presence, a quiet anchor in the restless sea of space-time.